Tonight, we're going to explore something that will completely reshape how you understand reality itself. We're going to discover the true nature of the cosmos, from the tiniest quantum fluctuations to structures billions of light years across. Not just the facts you might have heard before, but what those facts actually mean. By the end of this journey, you're going to understand mysteries so profound that they challenge everything we think we know about existence. Before we start, if you enjoy these deep explorations of the cosmos, a quick like or subscribe would really help the channel grow. Now let's begin our journey into the deepest mysteries of the universe, the observable universe, and what lies beyond. Let's start with something fundamental. When you look up at the night sky, you're seeing light that has traveled through space for varying amounts of time. The moon's light takes about 1.25 seconds to reach your eyes. Sunlight takes roughly 8 minutes and 20 seconds. The light from the nearest star beyond our sun, Proxima Centauri, has been traveling for over 4 years, but that's just the beginning. The observable universe, the sphere of space from which light has had time to reach us since the Big Bang, extends about 46.5 billion light years in every direction. That's not a mistake. Even though the universe is only about 13.8 billion years old, the observable universe has a radius larger than that because space itself has been expanding. The light we see from the most distant galaxies was emitted when those galaxies were much closer to us, but space has been stretching ever since, carrying those galaxies away, while their ancient light traveled toward us through the expanding cosmos. This counterintuitive result comes from the nature of cosmic expansion. When we say space expands, we mean that the distance between distant objects increases over time, even if those objects aren't moving through space. It's not that galaxies are flying apart through a static space. Space itself is growing, carrying the galaxies along with it. An often used analogy is a balloon with dots on its surface. As you inflate the balloon, every dot moves away from every other dot, not because the dots are moving across the surface, but because the surface itself is stretching. The expansion rate is described by the Hubble constant, which tells us how fast space is expanding at any given time. Currently, the expansion rate is about 70 kilometers per second per megaparsec. This means that for every megaparsec of distance, about 3.26 million light years, the recession velocity increases by 70 kilometers per second. A galaxy 100 megaparsecs away recedes at 7,000 kilometers per second. A galaxy 1,000 megaparsecs away recedes at 70,000 kilometers per second. And galaxies far enough away recede faster than the speed of light. This doesn't violate relativity. Nothing is moving through space faster than light. Rather, space itself is expanding so rapidly at great distances that the recession velocity exceeds light speed. This means that light from those galaxies can never reach us. They lie beyond our cosmic horizon. As the universe ages and expansion continues, more galaxies will cross this horizon and disappear from view. The observable universe is shrinking in terms of what we can eventually see, even though the physical size of the sphere from which we can currently receive light is still growing. There are actually two important horizons to consider. The particle horizon defines the edge of the observable universe, the maximum distance from which light could have reached us given the age of the universe and its expansion history. This is the 46.5 billion light-year radius sphere. The event horizon, in a cosmological sense, defines the boundary beyond which events happening now will never be observable to us in the future, no matter how long we wait. If dark energy remains constant or strengthens, this event horizon is closer than the particle horizon. Galaxies beyond the event horizon are already out of reach. We can see them now, observing their past light, but we will never see what they're doing at this moment or in their future. Within this observable sphere, we can count roughly 2 trillion galaxies. Each galaxy contains anywhere from millions to trillions of stars. The numbers become so vast that they lose meaning. If you tried to count all the stars in the observable universe at a rate of 1 per second, never stopping to eat, sleep, or rest, you would need far longer than the current age of the universe to finish counting. The total number of stars is estimated at around 200 billion trillion, or 200 sextillion. That's a 2 followed by 23 zeros. But the observable universe is merely a horizon, a boundary, a limit imposed by the speed of light and the finite age of the cosmos. Beyond that horizon, space continues. We have no way of knowing how far. The universe might be infinite. It might curve back on itself. It might be one bubble in an endless multiverse. These are not idle speculations, but serious scientific possibilities being actively explored by physicists and cosmologists around the world today. The cosmic microwave background, the oldest light we can observe, comes from a shell at the edge of the observable universe. This light was released about 380,000 years after the Big Bang, when the universe cooled enough for neutral atoms to form, and photons could travel freely. Before that moment, the universe was opaque, a hot plasma where light scattered continuously off free electrons. The cosmic microwave background represents our ultimate horizon. We cannot see beyond it with light. Everything that happened before that moment, the first 380,000 years of cosmic history, is hidden from direct observation. We infer what happened through physics and mathematics, but we cannot observe it directly. This creates one of the first great mysteries. What happened? In those first moments, how did the universe begin? What existed before the Big Bang, if anything? These questions lead us into territory where observation ends and theoretical physics takes over. The answers physicists propose are stranger than anything imaginable, involving quantum fluctuations, infinite inflation, and the possible creation of countless universes beyond our own. The scale of the observable universe already defies comprehension. But when we consider what might lie beyond, when we contemplate the possibility of infinite space or an endless multiverse, we confront ideas that push our minds to their limits. Yet these are the questions science asks. These are the mysteries we're going to explore tonight. Black holes, nature's ultimate enigma. Among all the objects in the universe, black holes stand apart as perhaps the most extreme. They are regions where gravity becomes so intense that nothing, not even light, can escape once it crosses a boundary called the event horizon. They represent the ultimate endpoint for the most massive stars, and they challenge our understanding of physics in ways few other phenomena can. The concept of black holes emerged from Einstein's general theory of relativity, published in 1915. Einstein's equations describe how mass and energy warp the fabric of space-time. Normally, this warping is gentle. Earth curves space-time just enough to keep the moon in orbit. The sun's curvature keeps the planets circling. But when enough mass concentrates in a small enough region, the curvature becomes extreme. It curves so intensely that it creates a one-way surface in space-time. Objects can fall in, but nothing can escape back out. This is the event horizon. The name black hole is fitting. These objects are black because they emit no light. Any light falling toward them gets pulled in and trapped forever. They are holes in the sense that they represent regions of space-time that are fundamentally disconnected from the rest of the universe. Once something crosses the event horizon, it's gone from our universe in a very real sense. We can never observe it again. We can never receive signals from it. It has passed beyond a boundary that cannot be crossed from the inside. Black holes come in several varieties. Stellar mass black holes form when massive stars, those with at least 20 to 25 times the mass of the Sun, exhaust their nuclear fuel and collapse. Throughout a star's life, nuclear fusion in its core creates outward pressure that balances the inward pull of gravity. This delicate balance, called hydrostatic equilibrium, maintains the star's structure for millions or billions of years, depending on its mass. A massive star burns through its fuel much faster than smaller stars. While the Sun will shine for about 10 billion years, a star 25 times more massive might live only 7 million years. The reason is that more massive stars must generate more pressure to support their greater weight. This requires higher core temperatures, which accelerates nuclear fusion dramatically. The star burns bright, but dies young. During its life, a massive star goes through several burning stages. It starts by fusing hydrogen into helium in its core. When the core hydrogen is exhausted, the core contracts and heats up. This ignites helium fusion, producing carbon and oxygen. The outer layers expand, and the star becomes a supergiant, hundreds of times larger than the Sun. After helium burning, the core contracts again, reaching temperatures where carbon can fuse into neon and magnesium. This continues through successive stages, each burning a different element: neon, oxygen, silicon, producing heavier and heavier elements. Each stage happens faster than the previous one because heavier elements yield less energy when fused. The final stage is silicon burning, which produces iron. Iron is where the chain ends. Fusing iron doesn't release energy. It consumes energy instead. Once the core fills with iron, fusion can no longer support the star. The core has reached the end of the line. At this point, the core might contain about 1.5 to 2 solar masses of iron, nickel, and other heavy elements, compressed to incredible densities and heated to billions of degrees. When fusion stops, gravity wins. The core collapses catastrophically. In less than a second, the core implodes from roughly the size of Earth to a sphere perhaps 10 kilometers across. The material falls inward at speeds approaching a quarter the speed of light. The collapse is so violent that electrons are forced into protons, producing neutrons and neutrinos. This process is called neutronization. For a brief moment, the density becomes comparable to that of an atomic nucleus, roughly 400 million tons per cubic centimeter. If the core is massive enough, around 3 times the Sun's mass or more, no known force can halt the collapse. The neutron degeneracy pressure, which can support neutron stars up to about 2 to 3 solar masses, is insufficient. The core compresses beyond the density of atomic nuclei, beyond the density of neutron stars, collapsing into a singularity, a point of infinite density at the center of a black hole. The outer layers of the star explode outward in a supernova, one of the most energetic events in the universe, but the core continues collapsing inward. Within a fraction of a second, it forms an event horizon. A new black hole is born. The process releases tremendous energy, but the black hole itself is dark and silent. It simply exists, warping space-time around it, waiting for matter to fall in. The supernova explosion itself is spectacular. The core collapse releases an enormous amount of gravitational potential energy, roughly 10 to the 53 ergs, or about 100 times the energy the Sun will emit over its entire 10 billion year lifetime. Most of this energy goes into neutrinos, ghost-like particles that barely interact with matter and stream away from the collapsing core at nearly the speed of light. A small fraction, about 1%, goes into the kinetic energy of the explosion, blasting the star's outer layers into space at speeds of tens of thousands of kilometers per second. The explosion enriches the interstellar medium with heavy elements forged in the star's core during its life and in the explosion itself. Elements like oxygen, silicon, sulfur, and iron are created through nuclear fusion in the star's core. Even heavier elements, including gold, platinum, and uranium, are synthesized in the intense neutron-rich environment of the supernova explosion through a process called rapid neutron capture, or R process. These elements are scattered into space, mixing with the surrounding gas. Future generations of stars form from this enriched material, and rocky planets like Earth can form, built from the ashes of long-dead stars. Supermassive black holes occupy the centers of most large galaxies. These monsters contain millions or billions of times the mass of the Sun. The Milky Way's central black hole, Sagittarius A star, has a mass of roughly 4 million suns. The black hole at the heart of the Messier 87 galaxy weighs about 6.5 billion solar masses. These objects didn't form from collapsing stars. They're far too massive. Their origins remain somewhat mysterious, though current evidence suggests they grew over billions of years by consuming gas, stars, and merging with the other black holes. Some theories propose they formed from the direct collapse of massive gas clouds in the early universe, while others suggest they began as stellar mass black holes that grew through continuous accretion. In 2019, the Event Horizon Telescope collaboration released the first ever image of a black hole's shadow. The image showed the supermassive black hole in Messier 87, a galaxy 55 million light-years away. The black hole itself is invisible, but the image captured the silhouette of the event horizon against the glowing disk of superheated matter swirling around it. This disk, called an accretion disk, shines brilliantly because friction heats the infalling material to millions of degrees. The material radiates across the electromagnetic spectrum, from radio waves to X-rays. The black hole's gravity bends the light from the disk, creating a bright ring around the dark shadow. That image confirmed predictions made decades earlier. It showed that black holes exist exactly as general relativity describes them. The size of the shadow matched theoretical calculations based on the black hole's mass. The shape was circular, as expected for a non-rotating or slowly rotating black hole. Later analysis revealed that the black hole was actually spinning, though not at its maximum possible rate. In 2022, the Event Horizon Telescope released a second image, this time of Sagittarius A star, the black hole at our galaxy's center. This was a more difficult target because it's much smaller and the matter around it varies on timescales of minutes. The team had to combine observations taken over several hours, and use sophisticated algorithms to reconstruct the image. The result was similar to Messier 87 in structure, a bright ring around a dark shadow, confirming that our own galaxy harbors a supermassive black hole at its heart. Recent discoveries have pushed our understanding of black holes even further. In November 2023, gravitational wave detectors observed the merger of two black holes that created a final black hole with a mass of approximately 225 times the Sun. This was the most massive black hole merger ever detected through gravitational waves. The two original black holes weighed around 100 and 140 solar masses, respectively. These masses fall within or near the theoretical mass gap, a range where black holes are thought to be difficult to form through normal stellar evolution. Their existence challenges current models of how massive stars die and how black holes are born. The black holes were also spinning rapidly, close to the maximum allowed by general relativity. Rapidly spinning black holes are more challenging to detect and analyze because their dynamics are more complex. The gravitational waves they emit during merger have specific signatures that depend on the masses and spins of the black holes involved. By analyzing the waveforms, scientists can extract detailed information about the black hole's properties and test predictions of general relativity under extreme conditions. In October and November of 2024, gravitational wave detectors captured two particularly unusual black hole mergers. The first, designated GW 42111, occurred about 700 million light years away. The merger involved black holes weighing roughly 20 and 6 times the Sun's mass. What made this merger special was the extremely rapid spin of the larger black hole. Its spin was one of the largest and most precisely measured among all gravitationally detected black holes. The second merger, GW 2411110, happened about 2.4 billion light years away. It involved black holes of 17 and 8 solar masses. This merger was notable because the primary black hole appeared to be spinning in the opposite direction from the orbit. This was the first time such counter-rotating behavior had been directly observed in a black hole merger. These unusual spins suggest that at least some black holes may be second-generation objects, based on current theoretical models. This would mean they could themselves be the products of earlier mergers. When two black holes merge, the resulting black hole receives a kick from the asymmetric emission of gravitational waves. This kick can be strong enough to eject the newly formed black hole from its birthplace. However, in dense environments like the centers of galaxies or globular clusters, the kicked black hole might remain gravitationally bound and eventually encounter another black hole, leading to a second merger. If correct, this interpretation would help to explain hierarchical mergers that can produce black holes with rapid spins and masses that are difficult to account for through single-star evolution alone. In January 2025, detectors recorded what may be the clearest gravitational wave signal ever observed, designated GW25114. The signal had an extraordinary signal-to-noise ratio of about 77 to 80, nearly double the previous record. The merger involved two black holes of 33.6 and 32.2 solar masses, producing a final black hole of 62.7 solar masses. The energy released in gravitational waves was equivalent to 3.1 solar masses, converted entirely to energy. The clarity of the signal allowed scientists to detect the first overtone of the black hole's ring down. the phase after merger when the newly formed black hole vibrates like a struck bell before settling into a stable state. This overtone is predicted by general relativity and specifically by mathematician Roy Kerr's description of rotating black holes, but it had never been clearly observed before. The measurement also confirmed Hawking's area theorem, which states that the total surface area of a black hole can never decrease. In this merger, the two original black holes had a combined surface area of about 240,000 square kilometers. The final black hole had a surface area of about 400,000 square kilometers, confirming the theorem with unprecedented precision. At the heart of every black hole, according to general relativity, lies a singularity, a point where the density becomes infinite and the known laws of physics break down. The equations predict that all the mass of a black hole is compressed into this single point of zero volume. At the singularity, the curvature of space-time becomes infinite. Our equations return nonsensical results. This is where general relativity meets its limit. The theory can describe the curved space-time outside the event horizon with exquisite precision, but at the singularity, it cannot tell us what happens. This breakdown suggests we're missing something fundamental in our understanding. Many physicists believe the singularity represents a place where quantum mechanics and gravity must be unified into a theory of quantum gravity. General relativity is a classical theory. It doesn't account for quantum effects. Quantum mechanics governs the behavior of particles and fields on small scales. When space curves so intensely that quantum effects become important at the Planck scale, around 10 to the negative 35 meters, we need a new theory that combines both. String theory, loop quantum gravity, and other approaches attempt this unification, but we don't yet have a confirmed theory of quantum gravity. The singularity remains a place of mystery, a boundary where our current knowledge ends. The event horizon itself poses fascinating questions. From an outside observer's perspective, nothing ever crosses the event horizon. Time dilation becomes so extreme near the horizon that, as viewed from afar, an infalling object appears to slow down asymptotically, approaching but never quite reaching the horizon. The object's light becomes increasingly redshifted, dimming and reddening until it fades from view. From the object's own perspective, however, nothing special happens at the horizon. It crosses in a finite amount of proper time. The object doesn't feel anything unusual. There's no barrier, no wall. The horizon is simply the boundary beyond which escape becomes impossible. Once across, the object continues falling toward the singularity. The time from horizon to singularity can be calculated using general relativity and is surprisingly brief, typically measured in microseconds for stellar mass black holes and hours for supermassive ones. This difference in perspective between the external observer who never sees anything cross and the infalling observer who crosses without incident highlights one of the strange features of black holes. Different observers experience space-time differently. This is a consequence of relativity. There is no single absolute time or space. Each observer has their own reference frame, and different frames can give different descriptions of the same event. Both descriptions are valid. This relativity of simultaneity becomes extreme near black holes, leading to seemingly paradoxical situations that nonetheless are perfectly consistent within general relativity. Black holes also emit a faint radiation through a quantum mechanical process discovered by Stephen Hawking in 1974. This Hawking radiation arises from quantum fluctuations near the event horizon. In quantum field theory, even empty space seethes with virtual particle-antiparticle pairs that pop into existence and annihilate almost instantly. Near the horizon, one member of a virtual pair can fall into the black hole while the other escapes. To an outside observer, the escaping particle appears as real radiation emitted by the black hole. The black hole loses a tiny amount of mass energy in the process. The temperature of Hawking radiation is inversely proportional to the black hole's mass. For stellar mass black holes, the temperature is unimaginably small, far colder than the cosmic microwave background. Such black holes absorb far more energy from their surroundings than they emit through Hawking radiation, so they grow rather than shrink. But for very small black holes, the temperature becomes significant. A black hole with the mass of a mountain would have a temperature of a few billion degrees and would evaporate in a relatively short time, cosmically speaking. As the black hole evaporates, it gets smaller and hotter, radiating faster. The final moments would be a brilliant flash of energy. Primordial black holes, if they exist, are hypothetical black holes that could have formed in the early universe from density fluctuations. These could have any mass, from subatomic to stellar or greater. If any were formed with masses around 1 billion tons, about the mass of a mountain, they would be evaporating right now through Hawking radiation, having lived for approximately the current age of the universe. The final stages of evaporation would produce detectable bursts of high-energy particles and radiation. Astronomers have searched for such bursts, but haven't found any, placing constraints on how many small primordial black holes could exist. The evaporation process leads to one of the deepest mysteries in physics, the black hole information paradox. Quantum mechanics states that information cannot be destroyed. If you know the exact quantum state of a system now, you can in principle calculate its state at any past or future time. The evolution of quantum systems is deterministic and reversible. But when a black hole evaporates, it seems to destroy information. Matter falls into the black hole, carrying information about its quantum state. That information disappears behind the event horizon. The black hole then evaporates away via Hawking radiation, which is thermal and carries no information about what fell in. At the end, the black hole is gone and the information seems to have vanished with it. This apparent violation of quantum mechanics troubled physicists for decades. Various resolutions have been proposed. Some suggest the information is somehow encoded in subtle correlations in the Hawking radiation. Others propose that information is stored at the event horizon in a two-dimensional holographic form. String theory suggests that black holes have enormous numbers of microscopic quantum states, and the information could be encoded in which state the black hole occupies. More recently, calculations involving the entropy of Hawking radiation have suggested that information does leak out very slowly as the black hole evaporates, with most of the information emerging in the final stages. The paradox remains an active area of research. It sits at the intersection of quantum mechanics, general relativity, and thermodynamics, and resolving it may require breakthroughs in our understanding of how these fundamental theories fit together. Black holes also provide natural laboratories for testing general relativity in extreme conditions. The gravitational fields near black holes are the strongest in the universe. The curvature of space-time reaches its maximum. Light bends dramatically. Time dilates enormously. By studying black holes through gravitational waves, X-ray emissions, and other observations, physicists can test whether Einstein's equations hold in these extreme environments. So far, every test has confirmed general relativity. The theory works extraordinarily well, from the weak gravitational fields of the solar system to the intense fields near merging black holes. Yet we know general relativity cannot be the final word. It predicts singularities where it breaks down. It doesn't incorporate quantum mechanics. At some level, a more complete theory must emerge. Black holes are places where we might find deviations from general relativity, hints of new physics. So far, we haven't. But as our instruments improve and we observe more black holes in more detail, we may eventually detect subtle effects that point toward quantum gravity or other extensions of our current theories. The information paradox and quantum mysteries. The information paradox is more than just a puzzle about black holes. It represents a fundamental conflict between two of our most successful theories, quantum mechanics and general relativity. Quantum mechanics governs the microscopic world of particles, atoms, and molecules. General relativity describes gravity and the large-scale structure of space-time. Both theories have been tested extensively and have passed every experimental challenge. Yet they seem to give contradictory answers about what happens to information in black holes. In quantum mechanics, information is never lost. The state of a quantum system evolves according to the Schrödinger equation, which is deterministic and reversible. If you know the quantum state at one time, you can calculate it at any other time, forward or backward. Even if a system becomes entangled or undergoes complex interactions, the information about its initial state is preserved in the correlations between particles or in the precise details of the final state. This preservation of information is deeply connected to the fundamental structure of quantum theory. If information could be destroyed, it would violate the principles that quantum mechanics is built upon. Black holes appear to violate this principle. When matter falls into a black hole, it carries quantum information with it. From the outside, we can measure the black hole's mass, spin, and electric charge, but that's all. The details of what fell in, the specific arrangement of particles, their quantum states, all of that is hidden behind the event horizon. John Wheeler summarized this with the phrase black holes have no hair, meaning they have no distinguishing features beyond mass, spin, and charge. Two black holes with the same mass, spin, and charge are identical, regardless of what formed them or what fell into them. As the black hole evaporates through Hawking radiation, the situation worsens. Hawking radiation is thermal, meaning it has the same character as the radiation from any hot object. Thermal radiation carries no information about the specific details of the object emitting it. A ton of coal burning at a given temperature emits essentially the same thermal radiation as a ton of wood at the same temperature. Similarly, Hawking radiation from a black hole of a given mass is always the same, regardless of what fell into that black hole. When the black hole finally evaporates completely, all that remains is thermal radiation that contains no trace of the quantum information that went in. This seems to violate quantum mechanics. The information has been lost. The evolution is no longer reversible. You cannot reconstruct the initial state from the final state. This paradox has generated decades of research and debate. Physicists have proposed various solutions, each with its own challenges. One early proposal was that information might be preserved at the singularity. Perhaps the singularity doesn't destroy the information, but stores it somehow. However, this idea has problems. Singularities are where our theories break down. We don't have a quantum theory of gravity to describe what happens there. Moreover, once the black hole evaporates, the singularity is presumably gone as well. Where did the information go? Another idea is that information might escape in subtle correlations in the Hawking radiation. While the radiation is thermal to a first approximation, perhaps there are tiny, almost imperceptible correlations between particles that encode the information. Early calculations suggested these correlations would be too small to carry all the information out before the black hole evaporated. But more recent work, particularly calculations involving the fine-grained entropy of Hawking radiation using the so-called replica trick and quantum extremal surfaces, suggests that information does escape, with the majority emerging in the late stages of evaporation. The radiation is not perfectly thermal after all. It contains subtle quantum entanglements that preserve information. The holographic principle offers another perspective. This principle, inspired by studies of black hole thermodynamics and developments in string theory, suggests that all the information within a volume of space could theoretically be encoded on a two-dimensional surface bounding that volume. For black holes, this would mean the information about everything that fell in might be stored on the event horizon itself. The horizon has a finite area, and according to this principle, the maximum entropy is proportional to that area measured in Planck units. This entropy represents the number of possible quantum states the black hole can occupy. As matter falls in, the black hole's mass increases, its horizon area grows, and its entropy increases. The information might be stored in the precise quantum state of the horizon, though exactly how this encoding works remains unclear. String theory approaches the problem from the perspective of microstates. In string theory, what we call a black hole is not a smooth object, but a bound state of an enormous number of fundamental strings and branes. The black hole's entropy corresponds to the number of different ways these strings and branes can be arranged while producing the same macroscopic properties: mass, spin, charge. There are so many possible arrangements that the number is astronomical, even for small black holes. The information about what fell in could be encoded in which specific microstate the black hole occupies. When the black hole evaporates, the information is released in the precise pattern of Hawking radiation corresponding to that microstate. Recent theoretical developments suggest that information is preserved and does escape from black holes, though the mechanism remains subtle and not fully understood. The process as currently theorized involves quantum entanglement between the Hawking radiation and the black hole's interior. As the black hole evaporates, entanglement gradually shifts from the interior to the exterior radiation. By the time the black hole has evaporated halfway, calculations indicate the radiation becomes more entangled with itself than with the remaining black hole. This transition, called the Page time, after physicist Don Page, who first calculated it, marks the point where information appears to start emerging more rapidly. The precise details depend on quantum gravity effects that we don't yet fully understand, and the complete resolution of the paradox remains an active area of research with competing theoretical approaches. The information paradox touches on deep questions about the nature of spacetime and quantum mechanics. It suggests that space and time, which appear smooth and continuous in general relativity, might be emergent phenomena arising from underlying quantum information. Space itself might be woven from entanglement between quantum degrees of freedom. When you alter the entanglement, you alter the geometry of space-time. This idea explored in approaches like the ER equals EPR conjecture, which connects Einstein-Rosen bridges, or wormholes, with Einstein-Podolsky-Rosen entanglement, hints that quantum mechanics and gravity are more deeply connected than we ever imagined. Black holes also raise questions about determinism and predictability. If information is lost, the evolution of the universe becomes fundamentally unpredictable. You could have two universes that are identical now but were different in the past because black holes destroy different information. This seems philosophically troubling and conflicts with quantum mechanics. If information is preserved but scrambled in complex ways, the universe remains deterministic in principle, but the extreme scrambling by black holes makes practical prediction impossible. The information is technically there, but extracting it would require knowledge and computational power, far beyond anything achievable. Another quantum mystery related to black holes is the firewall paradox. This paradox arises from considering the fate of an observer falling into an old, evaporating black hole. According to classical general relativity, the observer should cross the event horizon smoothly without experiencing anything unusual. The equivalence principle, a cornerstone of general relativity, states that freely falling observers don't feel gravity. As far as they're concerned, space is locally flat and normal. But quantum mechanics and the requirement that information be preserved seem to demand that the horizon is not smooth. Instead, it might be a firewall of high-energy particles that would incinerate any infalling observer. The firewall paradox arises from a conflict between three seemingly reasonable assumptions: the equivalence principle, the idea that information is not lost, and the idea that Hawking radiation is in a pure quantum state. You can preserve any two of these principles, but maintaining all three together appears to create contradictions. Physicists have debated which assumption should be abandoned. Abandoning the equivalence principle seems drastic, as it's fundamental to general relativity. Abandoning information conservation would violate quantum mechanics, allowing the radiation to be in a mixed state rather than pure seems to require giving up quantum mechanics unitarity. As of now, no consensus has emerged on which path to take, and some physicists question whether the firewall paradox represents a genuine problem or an artifact of our incomplete understanding. These paradoxes and puzzles highlight how little we truly understand about the intersection of gravity and quantum mechanics. Black holes force us to confront the limitations of our current theories. They show us places where general relativity and quantum mechanics give conflicting answers. The resolution will almost certainly require a new theory, a quantum theory of gravity that unifies these two pillars of modern physics. String theory, loop quantum gravity, and other approaches offer candidate frameworks, but none have been experimentally confirmed. We remain in a position where we can describe the universe with extraordinary precision in most circumstances, but at the extremes, in black holes, And at the beginning of the universe, our understanding breaks down. The Big Bang, origin of everything. The universe had a beginning. This was not always accepted. Through much of human history, many cosmologies assume the universe was eternal. Even after Einstein published general relativity in 1915, he initially thought the universe was static and unchanging. He added a cosmological constant to his equations to balance gravity and prevent the universe from collapsing. But observations would soon reveal that the universe is not static. In the 1920s, astronomer Edwin Hubble used the 100-inch telescope at Mount Wilson Observatory to study distant galaxies. By measuring the light from these galaxies, he made a revolutionary discovery. The galaxies were moving away from us. Moreover, the farther away a galaxy was, the faster it was receding. This relationship is now called Hubble's law. It shows that the universe is expanding. If the universe is expanding now, it must have been smaller in the past. Run the expansion backward, and you find that everything was compressed into an incredibly hot, dense state. This realization led to the Big Bang theory, the idea that the universe began in a hot, dense state and has been expanding and cooling ever since. The term Big Bang was actually coined by Fred Hoyle, a proponent of an alternative theory, in a somewhat derisive manner. But the name stuck. The Big Bang theory makes several key predictions that have been confirmed by observations. First, if the universe was once much hotter, it should have been filled with radiation. As the universe expanded, this radiation should have cooled. We should still be able to detect it today as a faint background glow filling all of space. This is the cosmic microwave background, discovered accidentally in 1965 by Arno Penzias and Robert Wilson. They were working with a radio antenna and detected a persistent noise coming equally from all directions in the sky. After ruling out all possible terrestrial sources, including pigeon droppings on the antenna, they realized they were detecting the afterglow of the Big Bang itself. The cosmic microwave background has a temperature of about 2.1726 Kelvin, just under 3 degrees above absolute zero. It corresponds to microwave radiation with a peak wavelength of about 1.9 millimeters. This radiation was released when the universe was about 380,000 years old. Before that time, the universe was so hot that electrons were not bound to atomic nuclei. The free electrons scattered photons constantly, making the universe opaque. Light couldn't travel far without hitting an electron. But as the universe expanded and cooled, electrons combined with protons to form neutral hydrogen atoms. This is called recombination, though it's a misnomer because the electrons and protons were combining for the first time, not recombining. Once electrons were bound into atoms, photons could travel freely. The universe became transparent. The photons from that era have been traveling through space ever since, gradually losing energy as the universe expanded. We observe them now as the cosmic microwave background. This background radiation comes to us from all directions, from a spherical shell surrounding us at a distance, corresponding to when the universe was 380,000 years old. In a sense, when we observe the cosmic microwave background, we are looking back in time to the surface of last scattering, the moment when the universe became transparent. The cosmic microwave background is remarkably uniform. Its temperature is the same in all directions to better than 1 part in 100,000. This uniformity posed a problem for the Big Bang theory. Regions of space on opposite sides of the sky, separated by billions of light years, have nearly identical temperatures. But according to standard Big Bang cosmology, these regions were never in causal contact. Light from one could never have reached the other. How then did they come to have the same temperature? This is called the horizon problem. Another puzzle is the flatness problem. The geometry of space can be curved or flat, depending on the total energy density of the universe. Observations show the universe is remarkably close to flat. But in standard Big Bang cosmology, flatness is an unstable equilibrium. If the universe started out even slightly curved, that curvature should have grown over time. To be as flat as we observe today, the universe must have been extraordinarily finely tuned to be flat at early times. Why should this be? The leading solution to these problems emerged from the theory of cosmic inflation, proposed in the early 1980s by physicists, including Alan Guth, André Linde, and others. According to this framework, the universe underwent a brief period of exponentially rapid expansion in its first moments, driven by a hypothetical field called the inflaton. During this period, which lasted perhaps 10 to the negative 32 seconds or so, the universe expanded by a factor of at least 10 to the 26 in size. This sounds absurd, but it solves several problems elegantly. Inflation solves the horizon problem because the entire observable universe today was once a tiny causally connected region. Before inflation, this region was small enough that light could traverse it, allowing different parts to come to the same temperature. Then inflation stretched this tiny region to enormous size. What had been a causally connected patch became larger than the observable universe. Regions that appear causally disconnected now were actually in contact before inflation. Inflation solves the flatness problem because exponential expansion flattens any initial curvature. Imagine inflating a balloon to enormous size. The surface of the balloon becomes increasingly flat over small regions. Similarly, inflation stretched the universe so much that any initial curvature was flattened out. After inflation, the universe was left extraordinarily close to flat, as we observe today. Inflation also explains the origin of structure in the universe. Quantum fluctuations in the inflaton field during inflation were stretched to macroscopic sizes. These fluctuations became the seeds of galaxies and galaxy clusters. The pattern of these fluctuations is imprinted on the cosmic microwave background as tiny temperature variations. These variations, detected by satellites like the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the Planck spacecraft, match the predictions of inflation remarkably well. The spectrum of fluctuations is nearly scale invariant, meaning fluctuations have similar amplitudes on different scales with a slight tilt. This is exactly what inflation predicts. The detailed measurements of the cosmic microwave background have become one of the most powerful tools in cosmology. By analyzing the pattern of temperature fluctuations, scientists can extract information about the composition and history of the universe. The data show that ordinary matter makes up only about 5% of the universe's total energy density. Dark matter accounts for roughly 27%. Dark energy makes up the remaining 68%. The data also constrain the geometry of space, the expansion rate, and other fundamental parameters with extraordinary precision. The Big Bang theory also makes predictions about the abundances of light elements produced in the early universe. During the first few minutes after the Big Bang, The universe was hot enough for nuclear fusion to occur. Protons and neutrons collided and fused, forming heavier nuclei. This is called Big Bang nucleosynthesis. The process lasted only a few minutes because the universe cooled rapidly as it expanded. By the time the temperature dropped below about 1 billion degrees, fusion stopped. The theory predicts specific abundances for light elements, about 75% hydrogen, 25% helium-4, and trace amounts of deuterium, heavy hydrogen, helium-3, and lithium-7. Observations of the oldest stars and gas clouds show abundances that match these predictions closely. The agreement is impressive and provides strong support for the Big Bang model. No other theory can explain the observed abundances as naturally. These three pillars, the expansion of the universe, the cosmic microwave background, and Big Bang nucleosynthesis, provide compelling evidence for the Big Bang theory. No other cosmological model explains all three as successfully. But what happened before the Big Bang? This question is inherently difficult, perhaps even meaningless in a physical sense. In the standard Big Bang model, time itself began at the Big Bang. Asking what came before is like asking what's north of the North Pole. There's no before, if time itself started. General relativity predicts that space-time has a boundary, a singularity at the beginning, where the density and temperature become infinite. At this singularity, our equations break down. We cannot describe the singularity using general relativity because the theory itself predicts its own failure at this point. Some cosmologists propose that the Big Bang singularity might be avoided in a complete theory of quantum gravity. Quantum effects could potentially smooth out the singularity, replacing it with a quantum bounce from a previous contracting phase. Models like loop quantum cosmology explore this possibility. In these models, the universe might cycle through phases of expansion and contraction, bouncing at a minimum size rather than collapsing to a singularity. However, these ideas remain highly speculative. We lack experimental evidence to support or refute them, and many theoretical questions remain unresolved. Another possibility is that our universe is one of many in an eternal inflation scenario. In this picture, inflation never truly ends globally, but continues in some regions while ending in others. Regions where inflation ends become bubble universes like ours. Outside these bubbles, space continues inflating forever, spawning new bubbles endlessly. According to this interpretation, each bubble could have different physical properties, different values for fundamental constants. This leads to the idea of a multiverse, which we'll explore later. However, whether eternal inflation actually occurs and whether other bubbles truly exist as separate universes remains a matter of theoretical debate. The timeline of the Big Bang is a story of cooling and transition. At the very beginning, fractions of a second after time zero, the universe was unimaginably hot and dense. Energy and matter were interchangeable. Particles and antiparticles popped into existence and annihilated constantly. Quarks, the building blocks of protons and neutrons, could not yet bind together because the temperature was too high. This was the quark-gluon plasma era. In these earliest moments, at times measured in tiny fractions of a second, the universe was governed by physics we can barely comprehend. At 10 to the negative 43 seconds, the Planck time, quantum gravitational effects dominated. This is where our theories completely break down. We have no quantum theory of gravity to describe what happened, The four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, may have been unified into a single force, though this remains speculative. As the universe expanded and cooled, these forces separated from each other in phase transitions. By 10 to the negative 36 seconds, the strong nuclear force had separated from the electroweak force. This separation may have triggered cosmic inflation, the exponential expansion that solved the horizon and flatness problems, though the exact mechanism remains uncertain. Inflation lasted perhaps until 10 to the negative 32 seconds, expanding the universe by a tremendous factor. When inflation ended, the energy driving it was converted into particles and radiation, reheating the universe to extremely high temperatures. From 10 to the negative 12 seconds to 10 to the negative 6 seconds, the electroweak force split into the electromagnetic force and the weak nuclear force. The Higgs field acquired its vacuum expectation value during this era, giving elementary particles their masses. Before this symmetry breaking, particles like electrons and quarks were massless and behaved very differently than they do today. At about 10 to the negative 6 seconds, or 1 microsecond, the temperature had dropped to about 10 trillion degrees Kelvin. At this point, quarks began to combine into protons and neutrons in a process called quark confinement. The quark gluon plasma transitioned into ordinary matter made of hadrons, particles composed of quarks. This transition was a phase change, similar to water freezing into ice, but occurring at energies far beyond anything we can create in laboratories. During the first microsecond, matter and antimatter existed in nearly equal amounts. But there was a slight asymmetry, about 1 extra matter particle for every billion matter-antimatter pairs. When matter and antimatter met, they annihilated into pure energy, producing photons. Almost all the matter and antimatter destroyed each other. The tiny excess of matter survived. This leftover matter makes up everything we see in the universe today, every star, planet, and galaxy. Why there was an asymmetry between matter and antimatter remains one of the great unsolved problems in physics. The standard model of particle physics includes processes that violate the symmetry between matter and antimatter, but calculations suggest not by enough to explain the observed imbalance. This implies something beyond the standard model must have been at work in the early universe. As the universe cooled through a temperature of about 1 trillion degrees, roughly 1 second after the Big Bang, conditions became cool enough for neutrinos to decouple from other matter. Neutrinos interact only through the weak nuclear force and gravity. So once the universe became diffuse and cool enough, neutrinos stopped colliding with other particles. They've been streaming freely through space ever since, forming a cosmic neutrino background, similar to the cosmic microwave background, but from an even earlier time. This neutrino background has never been directly detected because neutrinos interact so weakly, but its existence is a firm prediction of Big Bang cosmology. During the first 3 minutes, Big Bang nucleosynthesis occurred, forming light nuclei. Then the universe continued expanding and cooling. For the next 380,000 years, it remained opaque, a hot plasma of free electrons and nuclei. During this era, photons outnumbered matter particles by about 1 billion to 1. The universe was radiation dominated, meaning radiation provided most of the energy density. At 380,000 years, electrons combined with nuclei to form neutral atoms. The universe became transparent. Photons decoupled from matter and began streaming freely through space. These are the photons we observe as the cosmic microwave background. After recombination, the universe entered the matter-dominated era, where matter rather than radiation provided most of the energy density. For hundreds of millions of years, the universe was dark. No stars had formed yet. Hydrogen gas filled space, slowly collapsing under gravity into denser regions. This period is called the Cosmic Dark Ages, lasting from recombination at 380,000 years until the first stars ignited several hundred million years later. During the Dark Ages, the universe cooled as it expanded. The temperature dropped from about 3,000 Kelvin at recombination to perhaps a few dozen Kelvin. The gas remained neutral, mostly atomic hydrogen with some helium. Dark matter, unaffected by radiation, continued to clump under its own gravity, forming the first dark matter halos. These halos provided the gravitational wells where normal matter could accumulate. Gas fell into the dark matter halos, heating as it compressed. When the temperature and density became high enough, hydrogen fusion could ignite. The first stars were born. These population 3 stars, as they are called, were unlike any stars that exist today. They formed from primordial gas containing essentially no elements heavier than lithium. The lack of heavy elements profoundly affected how they formed and evolved. Without heavy elements, the gas had no efficient way to cool by radiation. Cooling is crucial for star formation because it allows gas clouds to contract under gravity. Modern star-forming clouds cool by radiating energy through emission lines from carbon, oxygen, and other elements, or through thermal radiation from dust grains. Primordial gas had none of these coolants. It could cool only through atomic hydrogen transitions, which are much less efficient. This inefficient cooling meant that primordial gas clouds had to be more massive before they could collapse to form stars. Theoretical calculations and computer simulations suggest that the first stars were very massive, perhaps tens to hundreds of times the sun's mass, much more massive than typical stars forming today. These massive stars burned extraordinarily hot and bright, with surface temperatures exceeding 50,000 degrees Kelvin and luminosities millions of times the sun's. These first stars lived fast and died young. A star 100 times the sun's mass might live only a few million years before exhausting its nuclear fuel. When they died, current models suggest they likely exploded as pair instability supernovae, extraordinarily powerful explosions that completely destroyed the star, leaving no remnant. The explosion would have blasted the star's ashes into surrounding space, enriching the primordial gas with the first heavy elements, carbon, oxygen, silicon, iron, and others forged in the star's core and in the explosion itself. However, we haven't yet directly observed any population 3 stars, so these scenarios remain theoretical predictions awaiting observational confirmation. This chemical enrichment fundamentally changed subsequent star formation. Gas enriched with even tiny amounts of heavy elements could cool more efficiently. This allowed smaller clouds to collapse, forming stars with a broader range of masses, including smaller stars like our Sun. Population 2 stars with low but non-zero metal content formed from this enriched gas. These are the oldest stars we can observe today in globular clusters and the halos of galaxies. Eventually, the first stars ignited. These stars were likely very massive and short-lived. They fused hydrogen into heavier elements and exploded as supernovae, enriching the gas with metals. This allowed the formation of subsequent generations of stars, including stars like our Sun that could host planets and eventually life. The ultraviolet light from these early stars had another critical effect. It ionized the surrounding hydrogen gas, creating bubbles of ionized plasma around each star or star cluster. These ionized bubbles expanded as more stars formed. Eventually, the bubbles overlapped, and the universe underwent a phase transition called reionization. The neutral hydrogen that filled space became ionized once again, similar to its state before recombination, but at a much lower density and temperature. Reionization was not instantaneous. Current models suggest it likely occurred gradually over several 100 million years, with observations indicating it may have started perhaps 150 million years after the Big Bang and completed by around 1 billion years. The James Webb Space Telescope is observing galaxies from this era, providing our first direct glimpses of the universe during and after reionization. These observations show that galaxies formed earlier and in greater numbers than previously thought, requiring revisions to our models of early structure formation. The first galaxies formed within the first billion years. We can observe these ancient galaxies with powerful telescopes, like the James Webb Space Telescope. They appear as they were when the universe was young, their light having traveled billions of years to reach us. These galaxies are smaller and more irregular than modern galaxies, still in the process of assembling through mergers and accretion. Over billions of years, galaxies grew larger through mergers and by attracting gas from their surroundings. Stars formed, lived, and died, enriching the interstellar medium with heavy elements. Supermassive black holes grew at the centers of galaxies. The large-scale structure of the universe emerged, with galaxies forming clusters and clusters linking into filaments surrounding vast cosmic voids. All of this structure traces back to the tiny quantum fluctuations during inflation, amplified by billions of years of gravitational growth. The Big Bang Theory is not just a model of the universe's past. It's a framework for understanding cosmic evolution, from the first moments to the present and into the future. It connects the smallest scales where quantum mechanics rules to the largest scales where galaxies and clusters form. It shows us that the universe has a history, a narrative arc from simplicity to complexity, from uniformity to structure, and it raises profound questions about origins, about why there is something rather than nothing, about whether our universe is unique or one of many. These questions drive cosmological research today. Cosmic inflation and the early universe. Cosmic inflation is one of the most important ideas in modern cosmology. It explains how the universe we observe today, with all its structure and uniformity, could have emerged from the Big Bang. But inflation is more than just a solution to cosmological problems. It's a window into physics at energies far beyond what particle accelerators can reach, and it leads to profound implications about the nature of reality itself. The core idea of inflation is that the universe underwent a period of exponentially rapid expansion in its earliest moments. This expansion was driven by a scalar field, the inflaton, which filled space with a nearly constant energy density. In general relativity, a constant energy density produces a repulsive gravitational effect, causing space to expand exponentially. The inflaton field sat at a high energy state, maintaining this constant density as space expanded. Then, after a brief period, the field rolled down to a lower energy state. Inflation ended, and the energy of the inflaton converted into particles and radiation, reheating the universe and beginning the standard hot Big Bang evolution. The details of how inflation started and how the inflaton field behaved are still uncertain. Many different models of inflation have been proposed, each with different predictions for observables, like the spectrum of density fluctuations and the production of gravitational waves. Observations, particularly of the cosmic microwave background, have constrained some of these models. The data favor models where inflation lasted long enough to solve the horizon and flatness problems and produced a nearly scale invariant spectrum of fluctuations with a slight red tilt, meaning slightly more power on large scales than small scales. One key prediction of inflation is the production of primordial gravitational waves. Quantum fluctuations during inflation affected not only the inflaton field, but also the metric of spacetime itself. These metric fluctuations became gravitational waves that propagated through the universe. The amplitude of these primordial gravitational waves depends on the energy scale of inflation. If inflation occurred at very high energies, the gravitational waves should be detectable in the polarization pattern of the cosmic microwave background. Specifically, they should produce a type of polarization called B-mode polarization. In 2014, the BICEP-2 experiment reported a detection of B-mode polarization that initially seemed to indicate primordial gravitational waves from inflation. This caused great excitement because it would confirm inflation and pin down the energy scale at which it occurred. However, further analysis, including data from the Planck satellite, showed that the signal was likely due to dust in our galaxy rather than primordial gravitational waves. The hunt for B-mode polarization continues with improved experiments, but as of now, no confirmed detection of primordial gravitational waves has been made. If primordial gravitational waves are detected, it would be one of the most important discoveries in cosmology, providing direct evidence for inflation and revealing the energy scale of the very early universe. Even without detecting gravitational waves, the evidence for inflation is strong. The uniformity of the cosmic microwave background, the flatness of space, and the specific pattern of density fluctuations all support the inflationary paradigm. The simplest alternatives to inflation struggle to explain these observations as elegantly. Some physicists have proposed alternative theories, such as bouncing cosmologies or ekpyrotic scenarios, where our universe is a brane in a higher dimensional space, but none have gained the same level of acceptance as inflation. Inflation also makes a striking prediction. The universe should be filled with nearly scale invariant Gaussian fluctuations. Gaussian means the fluctuations follow a random distribution with no preferred phase or special correlations beyond what randomness produces. Observations confirm this to high precision. The fluctuations in the cosmic microwave background are Gaussian, to better than 1 part in several thousand. There are slight deviations called non-Gaussianity that could reveal details about the physics of inflation, and experiments measure these deviations carefully. But the overall picture is that inflation produced a random Gaussian pattern of seeds for structure formation. The quantum origin of these fluctuations is one of the most remarkable aspects of inflation. In quantum mechanics, Fields fluctuate even in their ground state due to Heisenberg's uncertainty principle. During inflation, these quantum fluctuations in the inflaton field were stretched to macroscopic scales. What started as quantum jitters became classical density perturbations spanning millions of light years. These perturbations eventually collapsed under gravity to form galaxies and clusters. In a very real sense, the structure we see in the universe today, the galaxies, stars, planets, and life itself, all trace back to quantum fluctuations inflated to cosmic size. This connection between the quantum and the cosmic is one of the most profound insights in physics. The mechanism works like this. During inflation, space expanded exponentially. The quantum fluctuations that occurred during this period were stretched along with the expansion. As the wavelength of a fluctuation grew larger than the Hubble radius, the distance light could travel during the expansion time, the fluctuation froze out. It became a classical perturbation imprinted in the density field. After inflation ended, these frozen fluctuations became the seeds for structure formation. Regions that were slightly denser than average attracted more matter through gravity, growing denser over time. Regions that were slightly less dense lost matter, becoming voids. The amplitude of these fluctuations depends on the energy scale of inflation. Higher energy inflation produces larger fluctuations. The observed amplitude, about 1 part in 100,000, corresponds to an inflation energy scale around 10 to the 16 GeV, just below the energy scale where grand unification might occur. This gives us indirect information about physics at energies far beyond what we can probe directly with particle accelerators. The fluctuations are nearly Gaussian, meaning their distribution follows a bell curve with no significant skewness or special correlations. This is exactly what simple models of inflation predict. The inflaton field's quantum fluctuations are random, and when stretched to large scales, they produce a Gaussian distribution. Any significant deviations from Gaussianity, called non-Gaussianity, would tell us about more complex physics during inflation, perhaps multiple fields or non-standard interactions. So far, observations show the fluctuations are Gaussian to high precision, supporting the simplest inflation models. Inflation also raises deep questions about initial conditions. For inflation to work, the universe had to start in a specific state. The inflaton field had to be displaced from its minimum, sitting in a high energy state. The universe had to be smooth and homogeneous on small scales before inflation began. Why should these conditions hold? Some physicists argue that inflation is fine-tuned, requiring special initial conditions that seem unlikely. Others counter that inflation is robust. If it starts anywhere in a patch of space, it expands that patch so rapidly that it dominates the observable universe. Even if most of space is chaotic, one inflating region can grow to encompass everything we see. A related issue is the measure problem. In eternal inflation, inflation doesn't end everywhere at once. It ends in some regions, creating bubble universes, while continuing in others. The process goes on forever, producing infinitely many bubbles. How do we make predictions in such a scenario? If there are infinitely many of everything, how do we calculate probabilities? Different ways of counting, different measures, give different answers. This remains an unsolved problem in cosmology. Inflation connects to particle physics in interesting ways. The inflaton is a quantum field, similar to the Higgs field or the electromagnetic field. Understanding its properties requires understanding physics at very high energies, possibly near the scale of grand unification, where the electromagnetic, weak, and strong forces might merge into a single force. Particle physicists have proposed various candidates for the inflaton, including fields that arise in grand unified theories or string theory. But we don't know what the inflaton is. It remains a hypothetical field invoked to explain cosmological observations. Some models identify the inflaton with the Higgs field, the field responsible for giving particles mass in the standard model of particle physics. Higgs inflation is an attractive idea because it uses a field we already know exists. The Higgs field could have played a dual role, driving inflation in the early universe and giving particles mass later. However, for Higgs inflation to work, the Higgs field must couple to gravity in a specific way that differs from the standard coupling. Recent data from the cosmic microwave background have placed pressure on Higgs inflation. While still viable, the model is less favored than it was a decade ago. Another well-studied model is Starobinsky inflation, based on modifications to general relativity at high curvatures. In this model, the inflaton is not a new field, but an aspect of gravity itself. When space-time curvature becomes very high, general relativity could be modified by higher-order curvature terms. These terms can drive inflation. Starobinsky inflation makes specific predictions for the spectral index and the tensor-to-scalar ratio. Recent data, particularly from the Planck satellite and ground-based experiments, have tested these predictions. As of 2025, Starobinsky inflation remains compatible with observations, though the data are starting to place some pressure on certain versions of the model. The spectral index of density fluctuations, denoted NS, is a key observable that constrains inflation models. A perfectly scale invariant spectrum would have NS equal to 1. Most inflation models predict NS slightly less than 1, around 0.96 to 0.97. Recent measurements from the Planck satellite and other experiments indicate NS is approximately 0.965 to 0.968, with uncertainties at the sub-percent level. This rules out exact scale invariance at more than 8 standard deviations and strongly favors inflation models that predict a slight red tilt. The precision of this measurement is remarkable, constraining the physics of the very early universe to percent-level accuracy. The tensor-to-scalar ratio, denoted R, measures the amplitude of gravitational waves relative to density fluctuations. High-energy inflation produces more gravitational waves, giving larger R. The current upper limit on R from CMB polarization measurements is less than about 0.0036 at 95% confidence. This constrains the energy scale of inflation to below about 10 to the 16 GeV, just below the grand unification scale. If future experiments detect gravitational waves with R around 0.01, it would indicate inflation occurred at very high energies, possibly related to grand unification. If R remains below detection limits, inflation might have occurred at lower energies, or the model of inflation might be different from the simple single-field models commonly studied. Beyond solving cosmological problems and matching observations, inflation has philosophical implications. It suggests the universe is far larger than the observable region. Inflation expanded space so rapidly that regions outside our observable horizon were pushed beyond reach. We can never observe these regions because light from them hasn't had time to reach us, and due to continued expansion, never will. This means most of the inflated universe is forever beyond our view. We see only a tiny fraction of the whole. Furthermore, in many inflation models, the process becomes eternal. Once inflation starts, it's hard to stop everywhere at once. Quantum fluctuations can lift regions back into the inflating phase, even as other regions end inflation. This creates a fractal structure of inflating and non-inflating regions, with new bubble universes constantly forming. Each bubble is a universe unto itself, with its own initial conditions and potentially its own physical laws. This eternal inflation scenario leads naturally to the multiverse idea, which we'll explore in more detail later. The early universe was a laboratory for extreme physics. Conditions were so hot and dense that processes occurred that we can never replicate on Earth. By studying the remnants of those processes, encoded in the cosmic microwave background and the distribution of galaxies, we can learn about physics at energies far beyond our particle accelerators. Inflation connects the largest scales in cosmology to the smallest scales in particle physics. It shows us that understanding the universe's history requires understanding the fundamental laws of nature. And it reveals that the cosmos is stranger and larger than we ever imagined, with our observable universe, perhaps just one bubble in an infinite sea of universes. Dark matter, the invisible scaffold. One of the most profound mysteries in modern science is the existence of dark matter. We can't see it directly. It doesn't emit light. It doesn't absorb light. It doesn't interact with electromagnetic radiation in any way we can detect. Yet we know it's there because of its gravitational effects. Dark matter outweighs ordinary matter by a factor of about 6 to 1, making up roughly 27% of the universe's total energy content. The evidence for dark matter comes from multiple independent observations. In the 1930s, astronomer Fritz Zwicky studied the Coma cluster of galaxies. He measured how fast galaxies in the cluster were moving. Using the virial theorem, which relates the kinetic energy of a system to its gravitational potential energy, he calculated the total mass needed to hold the cluster together. The answer was surprising. The cluster's mass, based on the galaxy's motions, was far greater than the mass of the visible galaxies themselves. Zwicky proposed the existence of dark matter to account for the discrepancy. His work was largely ignored at the hour's time. In the 1970s, astronomer Vera Rubin and her colleagues measured rotation curves of spiral galaxies. A galaxy's rotation curve shows how fast stars and gas orbit the galactic center as a function of distance from that center. If most of a galaxy's mass were concentrated in the visible disk, you'd expect orbital speeds to decrease with distance, following Kepler's laws, just as planets orbit the sun. But Rubin found that rotation curves stayed flat, with orbital speeds remaining constant or even increasing at large radii. This meant galaxies contain far more mass than we can see, distributed in an extended halo around the visible disk. Dark matter can also be detected through gravitational lensing. According to general relativity, mass bends space-time, and light follows curved paths through that space-time. A massive object, like a galaxy cluster, acts as a lens, bending light from background galaxies. By studying the distortion of background galaxies' shapes, astronomers can map the distribution of mass in the foreground cluster. These maps show that clusters contain far more mass than can be accounted for by stars, gas, and dust. The extra mass is dark matter, distributed in large halos around the visible galaxies. One of the most dramatic pieces of evidence comes from the Bullet Cluster, a system of two galaxy clusters that collided. During the collision, the hot gas in each cluster interacted and slowed down, creating a shock wave visible in X-ray observations. But the dark matter in each cluster passed through without interacting, continuing ahead of the gas. By comparing the X-ray emission from the gas with gravitational lensing maps of the total mass, astronomers showed that most of the mass is not where most of the normal matter is. The dark matter halos are ahead of the gas clouds, demonstrating that dark matter is collisionless and distinct from ordinary matter. The cosmic microwave background also provides evidence for dark matter. The pattern of temperature fluctuations depends on the universe's composition. Dark matter affects how the universe expands and how structures grow. By fitting models to the CMB data, cosmologists can determine how much dark matter exists. The best fit models require dark matter to make up about 27% of the total energy density, consistent with other measurements. All of this evidence points to something invisible and massive exerting gravitational influence. But what is dark matter made of? That's the great mystery. It can't be ordinary matter, protons, neutrons, and electrons, because we can account for all the ordinary matter through Big Bang nucleosynthesis and observations of the cosmic microwave background. The amount of ordinary matter is about 5% of the universe's energy content. There simply isn't enough ordinary matter to account for dark matter. Dark matter must be something else. It must be made of particles that don't interact with light, that don't emit or absorb. Photons. These particles must be stable, or at least very long-lived, existing since the early universe. They must interact gravitationally, but their interactions through other forces, if any, must be extremely weak. Based on these requirements, physicists have proposed several candidates. One leading candidate is WIMPs, weakly interacting massive particles. These are hypothetical particles with masses ranging from about 10 to 10,000 times the proton's mass. They interact only through gravity and the weak nuclear force. The weak force is responsible for certain types of radioactive decay and operates only over subatomic distances. WIMPs would interact very rarely with ordinary matter. A WIMP could pass through the entire Earth without hitting a single atom. But occasionally, very occasionally, a WIMP might collide with an atomic nucleus, transferring a tiny amount of energy. This rare interaction is the basis for direct detection experiments. Scientists have built ultrasensitive detectors deep underground to search for these collisions. The detectors must be underground to shield them from cosmic rays, which would create false signals overwhelming any potential WIMP detections. The detectors are typically tanks filled with liquid xenon or other noble elements, surrounded by layers of shielding. When a WIMP collides with a xenon nucleus, the nucleus recoils, producing a tiny flash of light and sometimes ionization. The detectors measure these signals with incredible precision. The LX Zeppelin experiment, operating in a former gold mine in South Dakota, uses 10 metric tons of liquid xenon. The detector sits nearly a mile underground, shielded from cosmic radiation. It can detect recoil energies as small as a few electron volts, corresponding to incredibly gentle nudges of atomic nuclei. Despite years of operation and extraordinary sensitivity, Lux Zeppelin has not detected any clear WIMP signals. This null result doesn't prove WIMPs don't exist, but it does constrain their properties. If WIMPs exist and have the characteristics originally predicted, they must interact even more weakly than thought, or they must have different masses than the favored range. The Xenon T experiment in Italy uses a similar approach with 8 metric tons of liquid xenon. Panda X in China operates yet another large liquid xenon detector. All these experiments have reached similar conclusions. They're sensitive enough that they're now detecting neutrinos from the sun, radioactive backgrounds from traces of uranium and thorium in the detector materials, and even neutrinos from supernova processes in distant stars. These experiments have reached what's called the neutrino floor, the point where neutrino interactions become so common that they create a background noise, limiting further WIMP searches. To go beyond this requires new techniques or different approaches. The DAMIC-M experiment represents a different approach. Instead of using noble liquids, DAMIC-M uses silicon charge coupled devices, similar to digital camera sensors. These can detect the track of a recoiling nucleus with high spatial resolution. Early results from a prototype detector ruled out certain models of dark matter that invoke hidden sectors with new forces, demonstrating the power of diverse detection methods. As of 2025, the collaboration continues to refine its technology for future larger-scale experiments. Another major dark matter candidate is the axion, a hypothetical particle originally proposed to solve a problem in quantum chromodynamics called the strong CP problem. Axions, if they exist, would be extremely light, roughly a billionth to a millionth the mass of an electron. They would interact even more weakly than WIMPs, primarily through their coupling to photons in the presence of strong magnetic fields. Axion detection experiments use a clever technique. They place a resonant cavity inside a powerful magnet. If axions pass through the cavity, some could convert into photons due to the magnetic field. By tuning the cavity to resonate at the frequency corresponding to the axion's mass energy, the experiment can amplify the signal. The challenge is that nobody knows the axion's mass precisely, so experiments must search across a wide range of masses, tuning the cavity step by step. The Axion Dark Matter Experiment, or ADMX, has been searching for axions for over 2 decades. Based at the University of Washington, ADMX uses superconducting magnets and ultra-low noise amplifiers to achieve the sensitivity needed to detect axion conversions. The experiment scans frequency by frequency, ruling out axion masses where no signal appears. The haystack experiment at Yale University takes a similar approach, but focuses on higher frequencies, searching for heavier axions. The proposed MADMAX experiment aims to use a different detection method involving multiple dielectric disks to boost sensitivity. The CAST experiment at CERN takes yet another approach. It uses a decommissioned, large Hadron Collider magnet pointed at the sun. The idea is that axions could be produced in the sun's core and would stream outward. Some might convert to X-rays in the strong magnetic field of the CAST magnet. Detectors look for these X-rays as the magnet tracks the sun across the sky. So far, no confirmed axion signals have been detected, but the experiments continue to narrow the possible parameter space where axions might hide. Dozens of experiments around the world search for WIMPs. These experiments use detectors made of ultra-pure materials, cooled to near absolute zero, and placed deep underground to shield them from cosmic rays and other background radiation. When a WIMP scatters off a nucleus in the detector, it causes the nucleus to recoil, depositing a small amount of energy. This energy can be detected as heat, light, or ionization. The experiments are extraordinarily sensitive, capable of detecting recoils from individual WIMP collisions. Despite decades of searching, no experiment has made a confirmed detection of WIMPs. The lack of detection has ruled out large swaths of parameter space, the combinations of WIMP mass and interaction strength that are no longer viable. Some simple WIMP models that were once favored have now been excluded. However, many possibilities remain open. WIMPs could be lighter than initially expected, interact even more weakly than earlier models suggested, or have properties that make them harder to detect with current technology. The search continues with ever more sensitive detectors. The LWEX Zeppelin experiment in South Dakota, the Xenon T experiment in Italy, and the Panda X experiment in China are among the largest and most sensitive dark matter detectors currently operating. They use liquid xenon as the target material. When a particle interacts in the xenon, it produces scintillation light and ionization electrons. By measuring both signals, the experiments can distinguish dark matter events from background events. These detectors have reached sensitivities where they are starting to detect neutrinos from the sun and other sources. This neutrino background, called the neutrino floor, will soon become the limiting factor in WIMP searches. To push beyond the neutrino floor, detectors will need new technologies or new strategies to distinguish WIMPs from neutrinos. Another candidate is the axion, a very light particle proposed to solve a problem in the strong nuclear force called the strong CP problem. Axions, if they exist, would be incredibly abundant but extremely light, with masses billions of times smaller than the electron's mass. They would interact very weakly with ordinary matter, primarily through their coupling to photons. In the presence of a strong magnetic field, an axion can convert into a photon. This is the basis for axion detection experiments. Axion experiments use strong magnetic fields and sensitive microwave receivers to search for photons produced by axion conversions. The ADMX experiment at the University of Washington is one of the leading axion detectors. It uses a large superconducting magnet and an extremely sensitive receiver, cooled to near absolute zero. The experiment scans through different frequencies, looking for a signal that would indicate axion conversions. So far, no signal has been found, but the experiment has ruled out axions with certain masses and interaction strengths. Other experiments, including Haystack, MADMAX, and CAST, use different techniques to search for axions. The search space is vast, covering many orders of magnitude in possible axion masses, and only a small fraction has been explored so far. In recent years, dark matter searches have expanded beyond WIMPs and axions. Physicists are exploring a wider range of possibilities, including ultralight dark matter, sterile neutrinos, dark photons, and primordial black holes. Each candidate has different signatures and requires different detection methods. The field has become more diverse, reflecting the recognition that dark matter might not be a single type of particle, but could involve multiple components or unexpected physics. Ultralight dark matter, with masses far smaller than even the axion, could behave as a wave rather than as individual particles. These waves would oscillate with frequencies depending on the dark matter mass. Experiments are searching for the oscillating signals these waves would produce in precision measurement devices like atomic clocks. Dark photons, hypothetical particles similar to photons but with mass, could mediate a dark force that affects dark matter. Experiments search for dark photons by looking for their decays or interactions with ordinary matter. Sterile neutrinos, hypothetical cousins of ordinary neutrinos, might mix with regular neutrinos and decay in ways that could be detected. Primordial black holes formed in the early universe from density fluctuations are another candidate worth considering. These black holes could theoretically have any mass, from subatomic to stellar or beyond. If a significant fraction of dark matter consisted of primordial black holes, they could be detected through their gravitational lensing of background stars. Surveys searching for such lensing events have found some candidates, but not enough to account for all dark matter. Current constraints suggest primordial black holes might contribute to dark matter, but are unlikely to be the dominant component. The jury is still out on whether they play any significant role at all. The nature of dark matter remains one of the biggest open questions in physics. Its discovery would rank among the most important in the history of science. Not only would it reveal a new fundamental particle or class of particles, but it would also open a window into physics beyond the standard model. The current framework describing all known particles and forces, dark matter almost, certainly involves new physics, new particles, or forces that we haven't yet discovered. Understanding dark matter might lead to breakthroughs in particle physics, potentially revealing connections to other mysteries, like the nature of gravity at quantum scales or the unification of forces. Dark matter also plays a crucial role in cosmic history. In the early universe, dark matter began clumping together under gravity before ordinary matter could. Dark matter doesn't interact with radiation through photons, so it was free to collapse, while ordinary matter remained coupled to photons through electron scattering. This gave dark matter a head start in structure formation. Dark matter's gravity pulled ordinary matter into the potential wells it created, seeding the formation of galaxies. Without dark matter, the universe would look very different. Galaxies might not have formed, or they would have formed much later and been much smaller. The cosmic web of filaments and voids that we observe today is a direct consequence of dark matter's gravitational influence over billions of years. Simulations of cosmic structure formation rely on dark matter to reproduce the universe we observe. By varying the properties of dark matter in simulations, researchers can test how different candidates would affect galaxy formation and the large-scale structure. These simulations match observations remarkably well when they assume cold dark matter, meaning dark matter particles that move slowly compared to the speed of light. Hot dark matter particles moving at nearly light speed, like neutrinos, doesn't work as well because it can't form structures on small scales. Warm dark matter, an intermediate case, is still possible, but more tightly constrained. The ongoing search for dark matter is a testament to human curiosity and ingenuity. We're trying to detect something that doesn't want to be detected, that interacts so weakly with ordinary matter that it might pass through an entire planet without leaving a trace. Yet we persist because the evidence for its existence is overwhelming, and because understanding it is essential to understanding the universe. The answer, when it comes, will likely be surprising, revealing aspects of nature we haven't imagined. and it will open new questions, new mysteries to explore. Dark energy and the accelerating universe. In 1998, two independent teams of astronomers studying distant supernovae made a discovery that stunned the scientific community. They found that the universe's expansion is not slowing down under gravity's pull, as expected, but is actually accelerating. This acceleration implies the existence of something pushing space apart, a mysterious energy with negative pressure that fills the universe. This is dark energy. The two teams were the Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees. Both teams had been searching for distant Type Ia supernovae and measuring their properties with the goal of determining how much the universe's expansion had slowed since the Big Bang. The expectation was universal. Gravity from all the matter in the universe, both ordinary and dark, should be pulling everything back together, slowing the expansion. The only question was by how much. A universe with more matter would slow faster. By measuring the deceleration rate, the teams hoped to determine the total mass energy content of the universe. They observed dozens of supernovae in distant galaxies, some billions of light years away. These ancient explosions occurred when the universe was younger, billions of years in the past. By comparing these distant supernovae to nearby ones, the teams could measure how the expansion rate had changed over cosmic time. The process required extraordinary precision. The supernovae are faint, and their spectra complex. Measuring their redshifts and brightnesses accurately demanded the best telescopes and careful analysis. When the results came in, both teams found the same shocking answer. The distant supernovae were about 25% fainter than they should be if the expansion were slowing. They were farther away than expected. The only way this made sense was if the expansion rate had been increasing rather than decreasing. The universe was accelerating. The teams were initially skeptical of their own results. They checked everything. Could there be dust along the line of sight, dimming the distant supernovae? Dust absorbs and scatters light, which could make objects appear fainter and more distant. But dust also reddens light, preferentially removing blue wavelengths. The observations showed the supernovae had the expected colors, ruling out significant dust dimming. Could the distant supernovae be intrinsically different from nearby ones, perhaps because the chemistry of the universe was different in the past? Careful analysis showed the supernovae's properties were consistent across cosmic time. Could there be systematic errors in the measurements, subtle calibration issues, or selection biases? The teams scrutinized their methods exhaustively and could not find errors large enough to explain the results. After months of checking and cross-checking, the conclusion was inescapable. The acceleration was real. In early 1998, both teams published their findings. The universe was not just expanding, but speeding up. For this discovery, Perlmutter, Schmidt, and Rees shared the 2011 Nobel Prize in Physics. The discovery came from observations of Type Ia supernovae, explosions of white dwarf stars that serve as standard candles for measuring cosmic distances. Type Ia supernovae have remarkably consistent peak brightnesses. By comparing their apparent brightness to their known true brightness, astronomers can calculate how far away they are. By also measuring the supernova's red shifts, which indicate how much the universe has expanded since the light was emitted, astronomers can construct a relationship between distance and redshift. This relationship reveals the expansion history of the universe. If the universe's expansion were decelerating under gravity's pull, distant supernova would be brighter than expected because the universe expanded more slowly in the past than it does now. If the expansion were constant, the supernovae would appear at the brightness predicted by simple geometry. But the observations showed distant supernovae were dimmer than expected. This meant the universe expanded faster in the past than it would have if it were just coasting. The expansion was accelerating. This was completely unexpected. All forms of ordinary matter and energy exert attractive gravity, which should slow the expansion. An accelerating expansion requires something with repulsive gravity, something that pushes space apart rather than pulling it together. Einstein's equations allow for such a thing. A cosmological constant, a constant energy density inherent to empty space itself. Einstein had introduced the cosmological constant in 1917 to make the universe static. He later removed it when Hubble discovered the expansion. According to physicist George Gamow, Einstein later referred to it as his biggest blunder, though whether he actually used these exact words remains uncertain. But the cosmological constant is mathematically allowed in general relativity. It represents vacuum energy, the energy of empty space. In quantum field theory, even empty space is filled with quantum fields fluctuating in their ground states. These fluctuations contribute to the vacuum energy density. If this energy density is positive, it acts like a cosmological constant, creating a repulsive gravitational effect. The problem is that quantum field theory predicts a vacuum energy density far larger than observed. When physicists calculate the expected vacuum energy from quantum fluctuations, they get a value about 120 orders of magnitude larger than the observed dark energy density. This is one of the worst predictions in the history of physics. Why the vacuum energy is so much smaller than expected, yet not exactly zero, is called the cosmological constant problem. It's one of the deepest unsolved puzzles in theoretical physics. Despite this theoretical puzzle, observationally, dark energy behaves like a cosmological constant. Its energy density appears constant over time. It doesn't dilute as the universe expands, unlike matter or radiation. This constancy is what makes it act like vacuum energy. As the universe expands, the volume increases, but the dark energy density stays the same, so the total dark energy increases. This increasing energy drives the accelerated expansion. The evidence for dark energy extends beyond supernovae. The cosmic microwave background measurements show that the universe is spatially flat, meaning its total energy density equals the critical density needed to make space flat. But matter, both dark and ordinary, accounts for only about 32% of the critical density. Where's the rest? Dark energy fills the gap, making up the remaining 68%. The combination of supernovae, CMB, and large-scale structure observations all point to a universe dominated by dark energy. In recent years, however, new data have raised intriguing questions about whether dark energy is truly constant. The Dark Energy Spectroscopic Instrument, or DESI, began operations in 2021. It maps the three-dimensional positions of millions of galaxies and quasars, creating the largest three-dimensional map of the universe ever compiled. By analyzing this map, DESI measures the baryon acoustic oscillations, subtle patterns in the distribution of galaxies left over from sound waves in the early universe. These patterns provide a standard ruler for measuring cosmic distances and the expansion history. In 2024, DESI released its first-year results. The data hinted that dark energy might be evolving over time rather than remaining constant, though this remained far from confirmed. Specifically, the equation of state parameter, which characterizes dark energy's pressure relative to its density, appeared to change with cosmic time. A cosmological constant has an equation of state parameter of exactly -1. DC's data suggested the parameter might deviate slightly from -1 and vary over time. If this hint were confirmed by future data, it would mean dark energy is not a cosmological constant, but something dynamical. The significance of this result was about 3.9 standard deviations, or sigma, meaning there's roughly a 0.21% chance the deviation is due to random statistical fluctuation alone. While suggestive and intriguing, this falls short of the 5 sigma threshold, typically required to claim a discovery in physics. The result could be a genuine signal of new physics, or it could arise from systematic errors in the data or analysis, or it could simply be a statistical fluctuation that will disappear with more data. In 2025, DESI released its second data release, covering 3 years of observations. The preference for evolving dark energy strengthened slightly, reaching about 4.2 sigma. The combined results from DESI and other experiments, including the Dark Energy Survey and the Atacama Cosmology Telescope, show a consistent pattern favoring dynamical dark energy over a cosmological constant, though the statistical significance remains below the discovery threshold. If dark energy is indeed evolving, it would have profound implications. It would mean we need to revise our understanding of what dark energy is. A cosmological constant is the simplest possibility, but it's not the only one. Physicists have proposed various models of dynamical dark energy, often called quintessence. In these models, dark energy is a field, similar to the inflaton field that drove inflation that evolves over time. The field's potential energy acts as dark energy, but the field can roll to different values, changing the energy density and equation of state. Different quintessence models make different predictions for how dark energy evolves and for the universe's ultimate fate. If dark energy strengthens over time, the universe's expansion will accelerate ever faster, potentially leading to a big rip, where the expansion becomes so rapid that it tears apart galaxies, stars, planets, and eventually atoms. If dark energy weakens, the expansion might slow down, perhaps even reversing into contraction and leading to a big crunch. If dark energy remains roughly constant, the universe will continue expanding and cooling into a cold, dark, big freeze. Current data, even with the hints from DESI, are consistent with dark energy being nearly constant. The evolution, if real, is slow, but even slow evolution would be significant because it would rule out a cosmological constant and point to new physics. Understanding why the dark energy density is what it is and whether it changes could reveal deep truths about the universe's structure and fate. The nature of dark energy is one of the biggest questions in cosmology today. It makes up the majority of the universe's energy, yet we have no clear understanding of what it is or why it has the value it does. Upcoming experiments, including the Vera C. Rubin Observatory's Legacy Survey of Space and Time, NASA's Nancy Grace Roman Space Telescope, and ESA's Euclid satellite, will map billions of galaxies and measure cosmic expansion with unprecedented precision. These observations will either confirm that dark energy is a cosmological constant or reveal that it evolves, opening a new chapter in our understanding of the cosmos. Dark energy also connects to fundamental questions in theoretical physics. The cosmological constant problem suggests our current theories are incomplete. Perhaps quantum gravity effects modify the vacuum energy. Perhaps there are additional dimensions of space, as suggested in string theory, that affect the vacuum energy we observe. Perhaps our universe is one of many in a multiverse, and the dark energy value we measure is anthropically selected, meaning it has the value it does because only universes with this value allow for the formation of structures and observers like us. This anthropic reasoning remains controversial, as it shifts the question from why this value to why a multiverse with varying values. These are deep and speculative ideas, but they illustrate how dark energy pushes the boundaries of our knowledge. It's a reminder that despite all we've learned, the universe still holds secrets. Most of the universe's energy is in a form we don't understand. That's humbling, but it's also exciting. It means there are discoveries to be made, mysteries to solve, and that the quest to understand the cosmos is far from over. The multiverse and fine-tuning. Our universe appears finely tuned for life. The physical constants, the strengths of the fundamental forces, the masses of elementary particles, all seem precisely calibrated to allow for the existence of atoms, stars, planets, and ultimately life. Change any of these values slightly, and the universe would be dramatically different, likely unable to support complex structures or life as we know it. Consider the strength of the electromagnetic force relative to gravity. If electromagnetism were stronger, stars would burn out too quickly for life to evolve. If it were weaker, stars might not shine at all. The strong nuclear force, which binds protons and neutrons in atomic nuclei, has a strength that allows for a rich variety of chemical elements. Make it slightly stronger, and all hydrogen would have fused into heavier elements in the Big Bang, leaving no hydrogen for stars and water. Make it weaker, and heavier elements wouldn't form at all. Life. As we know, it depends on chemistry, which depends on having a range of elements from hydrogen to carbon, oxygen, and beyond. The cosmological constant is perhaps the most striking example of fine-tuning. As mentioned earlier, quantum field theory predicts a vacuum energy density 120 orders of magnitude larger than observed. If the cosmological constant were anywhere near that predicted value, the universe would have expanded so rapidly that galaxies, stars, and planets could never have formed. Structure formation requires gravity to overcome the expansion and pull matter together. With a large cosmological constant, the universe would expand faster than gravity could act. The fact that the observed cosmological constant is non-zero, but extraordinarily small compared to theoretical expectations, is a deep mystery. This fine-tuning has led to what's called the anthropic principle in various forms. The weak anthropic principle simply states that the universe must have properties compatible with the existence of observers because we are here to observe it. This is a tautology, but reminds us that we're not observing a random universe. We're observing one where intelligent life can exist, which necessarily means it has certain properties. The strong anthropic principle goes further, suggesting that the universe must have properties that allow life to develop at some stage in its history. This is more controversial because it seems to imply purpose or design, ideas that are not scientifically testable. The multiverse offers a way to address fine tuning without invoking design. If there are many universes with different physical constants, then it's not surprising that we find ourselves in one of the rare universes where the constants allow for life. We couldn't exist in the others. The multiverse idea emerges as a natural consequence from several areas of modern physics, though it remains deeply theoretical. Eternal inflation, as discussed earlier, would produce an infinite number of bubble universes if it occurred. Each bubble would end inflation at a different time and with potentially different properties. In some theoretical frameworks, the physical constants, or even the laws of physics, could vary between bubbles. String theory, a candidate for a theory of quantum gravity that has not been experimentally verified, appears to allow for an enormous number of possible vacuum states, perhaps 10 to the 500 or more, according to theoretical calculations. Each vacuum state would correspond to different physics, with different values for particle masses and force strengths. In what theorists call the string landscape, different regions of space might settle into different vacua, potentially creating a vast multiverse with varying physical laws. However, it's crucial to understand that string theory itself remains unconfirmed by experiment, and the existence of this vast landscape is a theoretical prediction rather than an established fact. If the multiverse exists, it changes how we think about fundamental questions. Why does the cosmological constant have its particular value? In a multiverse, it takes different values in different regions. We observe a small value because only in regions with small values can galaxies and life form. This is an anthropic explanation. It doesn't explain why the landscape of possibilities is what it is, but it explains why we observe what we do given that landscape. Critics argue that the multiverse is not scientific because we can never observe other universes. They are, by definition, beyond our cosmic horizon, causally disconnected from us. If we can't observe them or test the multiverse hypothesis, how can it be science? Proponents counter that the multiverse is a prediction of theories we can test, like inflation and string theory. If those theories are confirmed in other ways, we have reason to take their multiverse predictions seriously. There have been attempts to find observational evidence for the multiverse. One idea is to look for collisions between our bubble universe and others. If another bubble had collided with ours in the past, it might have left a signature in the cosmic microwave background, perhaps a circular feature or an unusual pattern of temperature fluctuations. Physicists have searched for such features in CMB data, but haven't found any convincing signals. The absence of clear collision signatures constrains some multiverse models, but doesn't rule out the multiverse altogether. It's possible that collisions are simply too rare, or that they occurred in regions beyond our observable horizon, or that the multiverse exists, but bubble collisions don't produce detectable signatures in the ways we've imagined. Another approach is to test inflation more precisely. If we can determine the details of how inflation occurred, we might be able to infer whether eternal inflation is inevitable. Detection of primordial gravitational waves, for example, would pin down the energy scale of inflation, and help distinguish between different inflationary models. Some models naturally lead to eternal inflation while others don't. By testing the models, we indirectly test the multiverse hypothesis. The fine-tuning problem also connects to questions about the origin of physical laws. Why do the laws of physics take the form they do? Why is there a standard model with 3 generations of particles, 4 fundamental forces, and specific coupling constants? These are questions that fundamental physics seeks to answer. Some physicists hope for a theory of everything, a single mathematical framework that uniquely predicts all the laws and constants. In such a theory, there would be no free parameters to tune. Everything would be determined by the underlying mathematics. String theory aspires to be such a theory, but it has not yet fulfilled that aspiration. The theory has many solutions, the landscape of vacua, each giving different physics. This is both a strength and a weakness. It's a strength because it might explain the appearance of fine-tuning through anthropic selection in a multiverse. It's a weakness because it doesn't make unique predictions. If any outcome is possible somewhere in the landscape, the theory loses predictive power. Other approaches seek to explain fine-tuning through emergent phenomena or symmetries. Perhaps the constants we observe are not fundamental, but emerge from deeper principles. Perhaps symmetries restrict the possible values, making the seemingly unlikely values actually natural. These ideas remain speculative, but they show the diversity of thinking about these problems. The question of whether our universe is unique or one of many has profound philosophical and existential implications. If we are alone, the universe's fine-tuning might seem miraculous or purposeful. If we are part of a multiverse, our existence is less surprising, but perhaps less significant. We become just one instance, among countless others, an accident of cosmic geography rather than a special creation. Yet this also gives a sense of humility and wonder. The cosmos might be far vaster and stranger than we can comprehend, with realities beyond our own, each with its own physical laws and possibilities. The multiverse also raises questions about the nature of reality and existence. Are all possible universes real in some sense? Do they exist physically, or are they merely mathematical abstractions? If they exist, where are they? In higher dimensional space? In parallel branches of quantum mechanics? These questions blur the line between physics, philosophy, and metaphysics. They remind us that science can take us to the edge of understanding, but cannot always provide definitive answers. Some questions may remain forever beyond our reach, not because we lack ingenuity, but because the nature of reality places limits on what can be known from within a single universe. Despite these uncertainties, the multiverse idea has become an important part of modern cosmology and theoretical physics. It offers a possible resolution to the fine-tuning problem, a framework for thinking about the initial conditions of the universe, and a prediction of some of our best theories. Whether it's true remains an open question, one that future observations and theoretical developments may help answer. Time, causality, and cosmic paradoxes. Time is one of the most familiar yet mysterious aspects of our experience. We perceive it flowing from past to future, moments passing irreversibly. Events have causes that precede them. This arrow of time seems fundamental to how the universe works. Yet at the deepest levels, the laws of physics are time-symmetric. The equations of motion, quantum mechanics, and even general relativity work equally well forward or backward in time. So where does the arrow of time come from? The answer lies in thermodynamics and entropy. Entropy is a measure of disorder or the number of possible microscopic states corresponding to a macroscopic state. The second law of thermodynamics states that in a closed system, entropy tends to increase over time. This is a statistical law. It's not that entropy must always increase, but it's overwhelmingly probable that it will, because there are far more high entropy states than low entropy states. Consider a gas in a container. If all the gas molecules start in one corner, that's a low entropy state. There are very few ways to arrange the molecules to have them all in one corner. As time progresses, the molecules spread out, filling the container. This is a high entropy state. There are many, many more ways to arrange the molecules so they fill the container evenly. The second law says the gas will almost certainly evolve toward higher entropy, spreading out rather than spontaneously collecting in a corner. This tendency toward increasing entropy gives time its direction. We remember the past, but not the future, because our brains are physical systems subject to the second law. Memories are low entropy structures, and forming them requires increasing entropy elsewhere. We see cups breaking, but not spontaneously reassembling, because the broken state has higher entropy. Irreversibility emerges from entropy increase. But this raises a puzzle. If the laws of physics are time symmetric, why is the universe in a low entropy state now? And why was it in an even lower entropy state in the past? The early universe, just after the Big Bang, was extraordinarily smooth and uniform. This uniformity is a low entropy state. High entropy states are lumpy and chaotic. As the universe evolved, gravity caused matter to clump into stars and galaxies. Paradoxically, gravitational systems have higher entropy when they're clumped. A diffuse gas has low gravitational entropy. A black hole has maximum entropy for a given mass. So the evolution from a smooth universe to one with galaxies and black holes is an increase in gravitational entropy. But why did the universe start in such a low entropy state? We don't know. This is called the problem of initial conditions, or the past hypothesis. One possibility is that inflation set up the low entropy state. Inflation flattens and smooths the universe, driving it toward a special low entropy state. But then we must ask, why did inflation occur? What set up the conditions for inflation? The question just pushes the problem back. We still need to explain why the universe, or the multiverse, or whatever preceded our universe, had the right properties to allow low entropy initial conditions. Some physicists propose that the arrow of time is related to the boundary conditions of the universe. Perhaps the universe began in a special low entropy state and will end in a high entropy state, the heat death. The asymmetry in boundary conditions gives time its direction. Others suggest that in an eternal multiverse or oscillating universe, different regions have different arrows of time, and we find ourselves in a region where entropy is increasing because that's where observers can exist. Time also behaves strangely near black holes and in strong gravitational fields. General relativity shows that time is not absolute. It passes at different rates for different observers, depending on their motion and gravitational environment. Near a black hole's event horizon, time dilation becomes extreme. For a distant observer, time appears to stop at the horizon. An infalling object seems frozen, never quite crossing. But from the infalling object's perspective, time proceeds normally and it crosses the horizon in finite proper time. Inside the event horizon, the roles of space and time swap. The radial direction toward the singularity becomes time-like, while the time direction becomes space-like. This means that inside the horizon, moving toward the singularity is as inevitable as moving forward in time. You can no more avoid the singularity than you can avoid the future. The singularity is not a place you hit, but a moment in time when space-time itself ends. General relativity allows solutions where causality becomes complicated or even seemingly violated. These are spacetimes containing closed time-like curves, paths through spacetime that loop back on themselves. If you follow such a curve, you would move forward in your own time at every instant, yet eventually return to an earlier point in time. This is the mathematical basis for time travel in general relativity. Several solutions of Einstein's equations contain closed time-like curves. The Gödel universe, discovered by mathematician Kurt Gödel in 1949, is a rotating universe where every point is connected by closed time-like curves. You could travel anywhere in space and time in such a universe, including visiting your own past. The interior of a rotating black hole, the Kerr solution, contains a region with closed time-like curves, traversable. Wormholes, if they could be stabilized, might allow travel between distant points in space and time, potentially creating loops in causality. But closed time-like curves create paradoxes. The most famous is the grandfather paradox. Suppose you travel back in time and prevent your grandfather from meeting your grandmother. Then you're never born. But if you're never born, you can't travel back in time to prevent the meeting. The paradox suggests that either time travel is impossible or something prevents paradoxes from occurring. One resolution is the Novikov self-consistency principle, proposed by physicist Igor Novikov. This principle states that if time travel is possible, events must be consistent. You cannot change the past because you didn't change it. If you traveled back in time, that event already happened. The timeline is self-consistent. You might try to prevent your grandparents from meeting, but something will always prevent you from succeeding. Maybe you change your mind or your actions somehow cause them to meet, or the gun jams at the crucial moment. The universe enforces consistency. Another approach involves many worlds or parallel universes. When you travel back in time, you enter a different branch of the quantum wave function or a parallel universe. You can change events there without creating a paradox in your original timeline. You prevent your grandfather from meeting your grandmother in this parallel universe, so a version of you is never born there. But in your original universe, you still exist. This avoids logical contradictions, but requires accepting a branching multiverse. Stephen Hawking proposed the chronology protection conjecture, a playful term for the idea that the laws of physics prevent time travel and the formation of closed time-like curves. According to this idea, whenever conditions approach those needed for time travel, quantum effects intervene to prevent it. For instance, trying to create a traversable wormhole that loops back in time might cause quantum vacuum fluctuations to become infinite, destroying the wormhole before it can be used. Nature, in effect, protects causality. The evidence suggests that chronology protection is real, though we lack a complete quantum theory of gravity to prove it rigorously. No closed time-like curves have been observed in nature, every known solution that contains them requires exotic conditions that seem unphysical. Traversable wormholes require exotic matter with negative energy density, which may not exist in the required quantities. Rotating black holes exist, but the regions with closed time-like curves are hidden behind event horizons and likely unstable. The Gödel universe describes a rotating cosmos, but our universe doesn't rotate on large scales. Based on current observations, it seems the universe does not permit time travel to the past, at least not in ways that would create paradoxes. General relativity allows for closed time-like curves, paths through space-time that loop back on themselves, allowing travel into the past. These arise in certain solutions of Einstein's equations, such as the Gödel universe, a rotating universe, or in spacetimes containing traversable wormholes. If closed time-like curves exist, they create potential paradoxes. The most famous is the grandfather paradox. If you travel back in time and prevent your grandfather from meeting your grandmother, you would never be born. But then you couldn't have traveled back in time to prevent the meeting. It's a logical contradiction. Various resolutions have been proposed. One is the Novikov self-consistency principle, which states that events must be self-consistent. If you try to change the past, something will always prevent you. You might intend to stop your grandparents from meeting, but you'll fail. Physical laws or accidents or your own actions will conspire to preserve consistency. The past cannot be changed because it has already happened and any attempt to change it was already part of history. Another resolution comes from quantum mechanics. In the many worlds interpretation, every quantum measurement branches the universe into multiple parallel realities. Time travel might create new branches. When you travel back and prevent your grandparents' meeting, you create a new timeline where you were never born. The original timeline where you were born and traveled back remains intact. Paradoxes are avoided because changes affect only the new branch, not the original one. However, most physicists believe closed time-like curves are either unphysical or at least inaccessible in practice. The energy conditions required to create traversable wormholes or other time machines appear to violate known physics. Creating such structures would require exotic matter with negative energy density, and it remains highly uncertain whether such matter can exist in sufficient quantities to build a time machine. Even if time machines are theoretically possible within the mathematics of general relativity, they might be unstable or might self-destruct before they can be used. Stephen Hawking proposed a chronology protection conjecture, suggesting that the laws of physics conspire to prevent time travel to the past, thereby preserving causality. While this remains unproven, many physicists find it plausible that nature has built-in safeguards against causal paradoxes. Causality, the idea that causes precede effects, is central to our understanding of the universe. If causality could be violated even in principle, it would undermine the very foundation of physics. We assume that events have causes and that we can trace chains of causation to understand why things happen. If time loops existed, this would break down. Effects could influence their own causes, creating feedback loops that are hard to analyze or predict. Quantum mechanics already challenges our notions of causality in subtle ways. In quantum entanglement, measuring one particle seems to instantaneously affect another, no matter the distance. This appears to violate causality, but it doesn't allow faster than light signaling. The correlations are established when the particles become entangled, and no information can be sent faster than light using entanglement alone. The apparent non-locality of quantum mechanics is real, but it doesn't break causality in a way that allows paradoxes. Another cosmic paradox is the nature of infinity. The universe might be infinite in spatial extent. If so, it contains infinitely many galaxies, stars, and planets. In an infinite universe, every possible arrangement of matter occurs infinitely many times. There are infinitely many copies of you, infinitely many versions of Earth, infinitely many of everything. This is strange but mathematically consistent. It's a consequence of having infinite space and finite matter density. Infinity also appears in the multiverse. Eternal inflation produces infinitely many bubble universes. If there are infinitely many universes, then again, every possibility occurs infinitely many times. This raises questions about probability and meaning. How do we make predictions in an infinite multiverse? If everything happens infinitely often, doesn't that make all probabilities equal? This is the measure problem mentioned earlier. It's an unsolved issue in cosmology and requires careful thought about how to define probabilities in infinite ensembles. Time, causality, and infinity are concepts that push our minds to their limits. They reveal the strange and counterintuitive nature of reality at its most fundamental. The universe doesn't conform to our everyday intuitions. It operates according to rules that are often surprising, sometimes paradoxical, but always fascinating. Gravitational waves and space-time ripples. Gravitational waves are ripples in the fabric of space-time itself, predicted by Einstein's general theory of relativity in 1916. For decades, they remained a theoretical curiosity, something predicted but never directly observed. That changed on September 14, 2015, when the LIGO detectors made the first direct detection of gravitational waves from a pair of merging black holes. This discovery opened a new window onto the universe, allowing us to observe cosmic events in an entirely new way. General relativity describes gravity not as a force, but as the curvature of space-time caused by mass and energy. When masses accelerate, they disturb the curvature, creating waves that propagate outward at the speed of light. These waves carry energy away from the source, and as they pass through space, they stretch and compress space-time itself. Gravitational waves are extraordinarily weak. Even the most violent events produce waves that cause only tiny distortions in space. The first detected gravitational wave signal from two merging black holes, each about 30 times the mass of the Sun, stretched and compressed space by less than 1 part in 10 to the 21. This is less than the diameter of a proton compared to the distance to the nearest star. Detecting such minuscule effects requires instruments of incredible sensitivity. LIGO, the Laser Interferometer. Gravitational Wave Observatory consists of 2 detectors, one in Hanford, Washington, and the other in Livingston, Louisiana. Each detector has 2 arms, each 4 kilometers long, arranged in an L shape. Laser beams travel down the arms and reflect off mirrors at the ends. When the beams return, they interfere with each other. If a gravitational wave passes through, it stretches one arm while compressing the other, changing the path lengths and altering the interference pattern. By monitoring this interference, LIGO can detect the passage of a gravitational wave. The first detection, called GW 50914, confirmed Einstein's prediction and demonstrated that black hole mergers occur. The signal matched the waveform predicted by general relativity. For two black holes spiraling together and merging, by analyzing the signal, scientists extracted the masses and spins of the black holes, the distance to the event, and confirmed that gravitational waves travel at the speed of light. The two black holes in GW5094 had masses of about 36 and 29 times the Sun's mass. They orbited each other, gradually losing energy to gravitational waves and spiraling closer. In the final fraction of a second, they reached orbital speeds exceeding half the speed of light. The waveform captured by LIGO showed the characteristic chirp pattern, increasing in frequency and amplitude as the black holes approached merger. At the moment of collision, the two black holes coalesced into a single black hole with a mass of about 62 solar masses. The missing 3 solar masses were converted entirely into gravitational wave energy, radiating away in a burst lasting less than a second. This energy release was greater than the combined light output of all the stars. In the observable universe, during that brief moment, the signal arrived at the Livingston detector 7 milliseconds before reaching Hanford, consistent with a gravitational wave traveling at light speed from a source in the southern hemisphere. This time, delay, combined with the signal amplitudes at both detectors, allowed scientists to estimate the source's location on the sky, though with considerable uncertainty due to having only 2 detectors. The source was determined to be about 1.3 billion light-years away, making it by far the most distant object ever directly observed at that time. The detection of GW1594 had profound implications beyond confirming gravitational waves. It proved that binary black hole systems exist, and that they merge on timescales comparable to the age of the universe. Before this detection, the existence of binary stellar mass black holes was uncertain. While binary stars are common, it wasn't clear whether both stars in a massive binary could collapse to black holes without the first supernova explosion disrupting the system. GW1594 showed it was possible. Since then, hundreds of black hole mergers have been detected, revealing a population of binary black holes throughout the universe. Since that first detection, LIGO and its partners, Virgo in Italy and Kagra in Japan, have detected hundreds of gravitational wave events. Most are black hole mergers, but some are neutron star mergers, or mergers between a neutron star and a black hole. Each detection provides a wealth of information about the sources and tests general relativity in extreme conditions. The inclusion of Virgo in the detector network dramatically improved sky localization. With 3 detectors operating simultaneously, scientists can triangulate the source position much more accurately than with 2. This is crucial for identifying electromagnetic counterparts, since telescopes need to know where to point to observe any light from the event. Kagra, the newest detector located in Japan, began operations in 2020, but has faced challenges reaching its design sensitivity. When fully operational, 4 detectors will provide even better localization and detection confidence. Different types of mergers produce different waveforms. Black hole mergers typically involve more massive objects and produce lower frequency gravitational waves with larger amplitudes. Neutron star mergers involve less massive objects and produce higher frequency signals with smaller amplitudes. The waveforms also encode information about the object's spins. A spinning black hole drags space-time around it, an effect called frame dragging. This affects the orbital dynamics and leaves imprints in the gravitational wave signal. By analyzing these subtle features, scientists can measure how fast and in what direction the black holes were spinning before they merged. One of the most significant detections came in August 2017. LIGO and Virgo detected gravitational waves from a neutron star merger designated GW70817. Within seconds, the Fermi and integral gamma ray satellites detected a short gamma ray burst from the same region of sky. This was the first time astronomers observed the same event in both gravitational waves and electromagnetic radiation. Within hours, telescopes around the world located the optical counterpart, a new point of light in the galaxy NGC 4993, about 130 million light years away. Over the following days and weeks, astronomers observed this kilonova across the entire electromagnetic spectrum, from gamma rays and X-rays, through ultraviolet, visible light, and infrared, all the way to radio waves. The multi-wavelength observations revealed extraordinary physics. The merger ejected material rich in neutrons at speeds up to 30% the speed of light. This neutron-rich material underwent rapid neutron capture, or R-process nucleosynthesis, forming heavy elements including gold, platinum, uranium, and other precious metals. Therefore, observations confirmed that neutron star mergers are the primary source of the universe's heavy elements. The gold in your jewelry, the platinum in catalytic converters, even the uranium in nuclear reactors, all came from neutron star mergers billions of years ago. The kilonova observations also measured the expansion rate of the universe independently of other methods. By combining the gravitational wave signal, which gives the distance to the source, with the redshift of the host galaxy measured from light, astronomers calculated the Hubble constant. This method, based on gravitational wave standard sirens, provides a completely independent check on other distance measurements and may help resolve discrepancies between different measurement methods. Gravitational waves provide information that electromagnetic observations cannot. Black hole mergers, for instance, emit no light. The black holes themselves are dark, and the merger happens too quickly for surrounding matter to produce detectable electromagnetic signals. Only gravitational waves can reveal these events. Similarly, gravitational waves can probe the interiors of neutron stars, regions hidden from electromagnetic observation by dense matter. The detected mergers also test general relativity. The waveforms of gravitational waves depend sensitively on the properties of spacetime around black holes and neutron stars. By comparing observations to theoretical predictions, scientists can check whether general relativity holds in strong field, high-velocity regimes. So far, every test has confirmed Einstein's theory with remarkable precision. Each gravitational wave detection carries information encoded in the waveform. The frequency evolution tells us about the masses and spins of the merging objects. The amplitude tells us how far away the event occurred. The polarization of the waves tells us about the orbital geometry. By carefully analyzing these properties, scientists extract detailed information about the sources. This is possible because general relativity makes precise predictions for what the waveforms should look like. The equations of general relativity can be solved numerically using supercomputers to simulate black hole mergers. These simulations produce template waveforms that match the observations extraordinarily well, providing some of the strongest tests of general relativity in extreme conditions. The agreement between theory and observation is remarkable. General relativity predicts specific relationships between different parts of the waveform. For example, it predicts how the frequency should increase as the objects spiral together, how the amplitude should peak at merger, and how the newly formed black hole should ring down afterward. Every one of these predictions has been confirmed by observations. This gives us confidence that we understand the physics of black hole mergers, and that general relativity correctly describes gravity even in these most extreme environments. In January 2025, LIGO detected a gravitational wave signal with the highest signal-to-noise ratio ever recorded, G/114. The clarity of this signal allowed scientists to detect subtle features that had been predicted but never clearly observed. They measured the first overtone of the black hole ringdown, confirming predictions about the vibrational modes of black holes. They also confirmed Hawking's area theorem with unprecedented precision, showing that the total surface area of the black hole increased after the merger, as required by thermodynamics and general relativity. Gravitational wave astronomy is still in its infancy. Future detectors like the Einstein telescope in Europe and Cosmic Explorer in the United States will be far more sensitive than current instruments. They will detect thousands of events per year, some from the early universe, and will open new frontiers in astrophysics and cosmology. Another future detector, the lasers, interferometer space. Antenna, LISA, will operate in space. LISA will consist of 3 spacecraft, arranged in a triangle, separated by millions of kilometers. It will detect gravitational waves at lower frequencies than ground-based detectors, sensitive to sources like supermassive black hole mergers, which occur in the centers of galaxies when galaxies merge. These events produce powerful gravitational wave signals lasting weeks or months. Detecting them will reveal the population of supermassive black holes, their growth over cosmic time, and their role in galaxy evolution. Pulsar timing arrays offer yet another method for detecting gravitational waves. Pulsars are rapidly rotating neutron stars that emit beams of radio waves. They are incredibly stable natural clocks. Gravitational waves passing through the galaxy alter the arrival times of pulsar signals in a correlated way across many pulsars. By monitoring an array of pulsars over years or decades, astronomers can detect the cumulative effect of gravitational waves, likely from a background of supermassive black hole mergers throughout the universe. Several pulsar timing arrays, including Nanograv in North America, have reported tentative evidence for such a background, though confirmation requires more data. Gravitational waves from the early universe could also exist. If inflation or other processes in the first moments generated gravitational waves, those primordial waves would still be propagating through space today. They would be imprinted on the cosmic microwave background as a specific pattern of polarization. Detecting this pattern would provide direct evidence for inflation and reveal the energy scale at which it occurred. Experiments like BICEP, the South Pole Telescope, and future satellites are searching for this signal. The study of gravitational waves complements and extends our understanding of the universe. It allows us to observe objects and events that are invisible to light, to test fundamental physics in regimes previously inaccessible, and to explore the universe's history in new ways. Every gravitational wave detection is a triumph of human ingenuity and persistence. It took a century from Einstein's prediction to the first direct detection, a century of developing the technology, refining the theory, and building the instruments. That achievement underscores the power of science to reveal the hidden workings of nature, cosmic voids, and the large-scale structure. On the largest scales, the universe is not uniform. Galaxies are not randomly scattered through space. Instead, they cluster together in groups and clusters, which link into vast filaments stretching hundreds of millions of light years. Between these filaments lie enormous, empty regions called cosmic voids. This cosmic web structure is one of the most striking features of the universe. The cosmic web emerged from the tiny density fluctuations in the early universe, the seeds planted by quantum fluctuations during inflation. As the universe expanded and cooled, gravity amplified these fluctuations. Denser regions attracted more matter, becoming denser still. Less dense regions lost matter to their surroundings, becoming voids. Over billions of years, this process created the structure we see today. Cosmic voids are vast regions with very few galaxies. The largest voids span hundreds of millions of light years. They're not completely empty, but have far lower densities than average. A typical void might contain only a few percent of the average galaxy density. The matter they do contain is mostly dark matter and gas, with very few stars or galaxies. Voids grow over time as matter flows out of them toward the surrounding filaments and clusters. This is counterintuitive. You might think expansion would cause voids to contract relative to the average, but the opposite happens. Gravity pulls matter from low-density regions toward high-density regions. The voids become emptier, while the filaments and clusters become denser. One of the largest claimed structures is the Hercules Corona Borealis Great Wall, a reported concentration of galaxy clusters and filaments that some studies suggest could stretch over 10 billion light years, though the exact size and whether it represents a true coherent structure remain subjects of scientific investigation. If confirmed at this scale, it would be so large that it challenges our understanding of structure formation. Cosmological simulations predict that structures this large should be exceedingly rare. Understanding such immense structures, if they exist as described, requires precise knowledge of dark matter, dark energy, and the initial conditions from inflation. Another intriguing large-scale feature is the KBC void, a region of lower than average galaxy density that some researchers suggest may encompass our local group. Some observations have been interpreted to indicate we might be located near the center of a void roughly a billion light years across. If this interpretation is correct, it could affect how we measure the expansion rate of the universe. Different locations in the cosmic web experience slightly different local expansion rates due to the gravitational effects of surrounding structures. Being in a void might bias our measurements, potentially contributing to discrepancies between different methods of measuring the Hubble constant. However, the existence and significance of the KBC void remain subjects of ongoing debate. Not all astronomers agree that this structure exists as described, and its properties and implications for cosmology are far from settled. The cosmic web's structure encodes information about the universe's composition and history. By measuring the distribution of galaxies on large scales, astronomers can constrain the amounts of dark matter and dark energy, test models of gravity, and check predictions of inflation. Surveys like the Sloan Digital Sky Survey, the Dark Energy Survey, and the upcoming Rubin Observatory Legacy Survey map millions of galaxies, creating three-dimensional maps of the cosmic web. These maps reveal the universe's geometry and evolution. Gravitational lensing also probes the large-scale structure. Light from distant galaxies is bent by the gravity of intervening matter, including dark matter in the cosmic web. By measuring how background galaxies' images are distorted, astronomers can map the distribution of dark matter on large scales. This technique, called weak gravitational lensing, reveals dark matter structures that are invisible to electromagnetic observations. The cosmic web is not static. It evolves over time as gravity continues to pull matter together. In the future, if dark energy remains constant or strengthens, the expansion will accelerate further. Filaments will stretch and eventually break apart. Clusters will become isolated, separated by ever-increasing distances. The cosmic web will gradually dissolve, leaving isolated islands of galaxies in an otherwise empty, expanding universe. The study of large-scale structure is also tied to the nature of dark matter. Different dark matter candidates produce different patterns of structure. Cold dark matter, which moves slowly and clumps efficiently, produces the hierarchical structure we observe, with small structures forming first and merging into larger ones. Warm dark matter, which moves faster, would smooth out small-scale structure, preventing the formation of dwarf galaxies and small-scale filaments. By comparing observations to simulations, astronomers can test different dark matter models. The cosmic web is a testament to the universe's evolution over billions of years. It shows how simple initial conditions, quantum fluctuations inflated to cosmic size, evolved under gravity into the complex, beautiful structure we see today. Every galaxy, every cluster, every void is part of this grand interconnected system, linked by gravity and cosmic history. The ultimate questions: heat death, Big Rip, and beyond. What is the ultimate fate of the universe? This question has fascinated humans throughout history. Ancient cosmologies often envisioned cyclical universes, with destruction followed by rebirth. Modern cosmology, based on general relativity and observational evidence, provides several possible scenarios. The fate depends on the nature of dark energy and the total energy density of the universe. If dark energy remains constant, a cosmological constant, the universe will continue expanding forever, with the expansion accelerating. Galaxies outside our local group are already moving away from us faster than the speed of light due to the expansion of space itself. We can't see the most distant galaxies because their light hasn't had time to reach us. As expansion continues, more and more galaxies will recede beyond our cosmic horizon, disappearing from view. Eventually, in hundreds of billions of years, only the galaxies gravitationally bound to our local group will remain visible. The Milky Way and Andromeda, having merged into a single galaxy called Milkdromeda, will be surrounded by darkness. The rest of the universe will be invisible, carried away by expansion. Future astronomers in this far future would see only their own galaxy, with no evidence of the wider universe. They might conclude that their galaxy is all there is. Star formation will continue for some time, but eventually the gas needed to make stars will run out. Stars will die, one by one. Massive stars will explode as supernovae, leaving behind neutron stars or black holes. Medium and low-mass stars will become white dwarfs, slowly cooling over trillions of years. Red dwarfs, the smallest and longest-lived stars, will burn for tens of trillions of years, but even they will eventually exhaust their fuel. The timeline of the far future can be divided into several eras, each characterized by different dominant processes. The stelliferous era, the current age of stars, will last until roughly 100 trillion years from now. During this era, star formation continues, though at a declining rate as gas is consumed. The peak of star formation actually occurred about 10 billion years ago, when the universe was roughly a quarter its current age. Since then, the star formation rate has been declining. Within the first trillion years, most galaxies will have exhausted their available gas. Stars will continue to form from recycled material. Gas returned to space by dying stars, but the overall rate will drop. Low-mass red dwarfs will dominate the stellar population because they live so long. More massive stars will have long since died. Galaxies will grow dimmer as their bright blue and white stars disappear, replaced by the faint red glow of dwarf stars. When the last stars die, the universe will enter the degenerate era, filled with stellar remnants, white dwarfs, neutron stars, and black holes. These objects will persist for an extraordinarily long time. White dwarfs will cool and become black dwarfs, inert lumps of matter no longer emitting light. Planets will remain in orbit around these remnants, frozen and dark. This era might last from 100 trillion years to perhaps 10 to the 40 years, depending on whether protons are stable. During the degenerate era, dynamical processes will continue, though extraordinarily slowly. Stars and planets in galaxies orbit the galactic center. Over time, close encounters between stellar remnants will redistribute energy. Some objects will gain energy and be ejected from the galaxy entirely, becoming intergalactic wanderers. Others will lose energy and sink toward the center. Eventually, most stellar remnants will either be ejected into intergalactic space or fall into the central supermassive black hole. This process, called dynamical relaxation, takes perhaps 10 to the 20 years for a typical galaxy. As the degenerate era progresses, even the cold stellar remnants will gradually disappear if protons are unstable. Current particle physics doesn't include proton decay, but many extensions of the Standard Model, particularly grand unified theories, predict that protons should decay with lifetimes around 10 to the 35 years or longer. If this is correct, then over vast time scales, all atomic matter will slowly disintegrate. White dwarfs and any remaining planets would gradually evaporate, converting to lighter particles like electrons, positrons, neutrinos, and photons. However, current experiments have only established that if protons decay, their lifetime exceeds 10 to the 34 years. We don't know whether protons are absolutely stable or merely very long-lived. If protons are stable, atomic matter would persist indefinitely, though spread increasingly thin by the universe's expansion. Whether or not protons decay, black holes will not last forever. Stephen Hawking's calculations showed that black holes slowly evaporate through quantum mechanical effects, emitting thermal radiation and gradually losing mass. The evaporation rate is incredibly slow. A solar mass black hole would take about 10 to the 67 years to evaporate completely. Supermassive black holes take even longer. A billion solar mass black hole would persist for roughly 10 to the 100 years. But eventually, even the largest black holes will evaporate, releasing their mass energy as radiation. The black hole era extends from roughly 10 to the 40 years to 10 to the 100 years. During this time, black holes are the dominant massive objects in the universe. They will have consumed much of the matter in galaxies, and many stellar mass black holes will have merged into larger ones. The universe will be dark except for the extremely faint Hawking radiation from evaporating black holes. When the last stars die, the universe will enter the degenerate era, filled with stellar remnants, white dwarfs, neutron stars, and black holes. These objects will persist for an extraordinarily long time. White dwarfs will cool and become black dwarfs, inert lumps of matter no longer emitting light. Planets will remain in orbit around these remnants, frozen and dark. Protons, the building blocks of atomic nuclei, might not be stable forever, according to some theoretical extensions of the Standard Model. These theories predict that protons could decay on timescales of 10 to the 35 years or longer. This is far beyond current experimental limits, and no proton decay has ever been observed despite decades of searching in underground detectors. But if protons do eventually decay, as some theories suggest, all atomic matter would gradually disintegrate. White dwarfs, neutron stars, and any remaining planets would slowly evaporate away over unimaginable timescales, leaving only electrons, positrons, neutrinos, and photons. However, this remains purely theoretical speculation. Protons might be absolutely stable, or their lifetime might exceed even the vast timescales we're discussing. Current experiments have only established that if protons decay, their lifetime must exceed 10 to the 34 years. Even black holes are not eternal. Through Hawking radiation, they slowly evaporate. The process is incredibly slow. A black hole with the mass of the Sun would take 10 to the 67 years to evaporate. Supermassive black holes would take even longer, 10 to the 100 years or more. But eventually, even the largest black holes will evaporate completely, their mass converted into radiation. After black holes evaporate, the universe will consist only of radiation and elementary particles, diluted by expansion to near zero density. The temperature will approach absolute zero. This is the heat death, a state of maximum entropy where no gradients exist, no energy flows, and no processes can occur. The universe will be cold, dark, and utterly lifeless. Time will still pass, but nothing will change. It's the ultimate fate predicted by the second law of thermodynamics in an ever-expanding universe. This timeline is incomprehensibly long. The current age of the universe is about 13.8 billion years. The era of star formation might last 100 trillion years. The degenerate era could extend to 10 to the 40 years. The black hole era lasts until 10 to the 100 years. The timescales involved dwarf not only human history, but the entire history of the universe so far. Yet if the universe is eternal, even these vast expanses are negligible. Eternity is long enough for anything to happen, no matter how improbable. If dark energy is not constant, but instead strengthens over time, the fate could be dramatically different. In some theoretical models, dark energy's repulsive effect could grow stronger, accelerating the expansion ever faster. Eventually, according to these models, the expansion could become so rapid that it overcomes the gravitational binding of clusters, galaxies, and eventually even stars, planets, and atoms. This is the big rip scenario, a theoretical possibility first explored in detail in the early 2000s. In a big rip scenario, galaxy clusters would be torn apart first. then individual galaxies, then stellar systems. As the expansion accelerates further, smaller and smaller structures would be ripped apart. Eventually, even atoms would be torn apart as the expansion rate exceeds the forces holding them together. The Big Rip would occur at a finite time in the future, determined by how rapidly dark energy strengthens. Current constraints on dark energy's evolution suggest that if a Big Rip is even possible, it would be many billions of years away. However, as we've discussed, the evidence for evolving dark energy remains tentative, and most data are still consistent with a cosmological constant that would never produce a Big Rip. Another possibility is the Big Crunch, where the expansion reverses into contraction. This would occur if dark energy weakens, or if the universe contains enough matter to halt and reverse the expansion. Current observations indicate the universe is flat and has more than enough dark energy to continue expanding forever. So a big crunch seems unlikely. But if dark energy turns into an attractive rather than repulsive force, the universe could recollapse. Galaxies would start moving toward each other. The cosmic microwave background would blue shift, becoming hotter. Eventually, the universe would collapse back into a hot, dense state, potentially leading to a singularity similar to the Big Bang in reverse. Some cosmological models propose a cyclic universe where big crunches might be followed by big bangs in an endless cycle. Each cycle could last trillions of years, with the universe expanding, collapsing, and somehow rebounding. However, these models face significant theoretical challenges, particularly regarding the growth of entropy. The second law of thermodynamics demands that entropy increase over time, but in a cyclic universe, how would entropy be reset with each cycle? Various proposals have been made to address this issue, but none have gained widespread acceptance, and many physicists remain skeptical that a truly cyclic cosmology can work within known physics. Another speculative idea is vacuum decay. Quantum field theory allows for the theoretical possibility that our current vacuum state is not the true ground state, but a metastable false vacuum. If this were the case, the vacuum could theoretically decay to a lower energy state through quantum tunneling. This decay would nucleate a bubble of true vacuum that expands at the speed of light, destroying everything in its path. Inside the bubble, the laws of physics might be fundamentally different, with different particle masses and force strengths. If vacuum decay were to occur, it would be sudden and catastrophic with no warning. The universe as we know it would cease to exist, replaced by a fundamentally different reality. The probability of vacuum decay depends on the properties of quantum fields, which we don't fully understand. Current theories suggest our vacuum might be metastable, meaning it could be stable enough to last for an extraordinarily long time, but not forever. However, the decay rate could be so low that it's extremely unlikely to occur within the observable universe's lifetime, or even within time scales trillions of times longer. The uncertainty in our understanding means we simply don't know whether this is a real threat or merely a theoretical curiosity. These scenarios, from heat death to Big Rip to vacuum decay, highlight the diversity of possible futures. They depend on unknown aspects of physics, the nature of dark energy, the stability of matter, the true vacuum state of the universe. Our understanding of the universe's fate is tied to our understanding of fundamental physics. As we learn more, our predictions will become more certain. Despite the cosmic timescales involved, these questions matter. They shape our understanding of reality, our place in the cosmos, and the ultimate meaning of existence. If the universe is doomed to heat death, does that render everything meaningless? Or does the journey matter more than the destination? These are questions science can inform but cannot definitively answer. They touch on philosophy, ethics, and human values. The universe's ultimate fate is a reminder that existence itself is temporary, that everything we know is transient on cosmic timescales. Yet here we are, conscious beings, capable of contemplating these vast questions. That alone is extraordinary. As we reach the end of this journey through the universe's greatest mysteries, we find ourselves with more questions than answers. We've explored black holes, where space-time curves to its breaking point. We've traced the universe back to its fiery origin in the Big Bang, witnessed the inflationary expansion that shaped everything we see. We've grappled with dark matter, the invisible scaffold holding galaxies together, and dark energy, the mysterious force accelerating cosmic expansion. We've listened to space-time itself ring with gravitational waves from colliding black holes. We've pondered the multiverse, the arrow of time, and the ultimate fate of everything. Each mystery deepens our wonder. Each answer reveals new questions. Black holes challenge our theories at their very limits. The Big Bang raises a question of what came before. Inflation hints at a multiverse we can never observe. Dark matter eludes our most sensitive detectors. Dark energy defies our theoretical expectations. The universe is stranger than we imagined, and perhaps stranger than we can imagine. Yet for all the unknowns, we've achieved something remarkable. We've measured the age and size of the universe. We've charted its history from the first fraction of a second to the present day. We've detected ripples in space-time itself. We've observed galaxies forming when the universe was young. We've tested Einstein's theories under extreme conditions and found them holding true. We've built a standard model of particles and forces that explains almost everything we observe. And we've discovered that the universe is dynamic, evolving, full of surprises. The mysteries we've explored tonight are not just puzzles to solve. They're invitations to think deeply about existence, reality, and our place in the cosmos. They remind us that we live in a universe that is ancient beyond measure, vast beyond comprehension, and governed by laws we are only beginning to understand. They show us that science is not about having all the answers, but about asking better questions, probing the unknown, and slowly, patiently revealing the hidden workings of nature. The universe doesn't owe us comprehensibility, yet we persist in trying to understand it. We build telescopes to see farther. We construct detectors to catch the faintest signals. We develop theories to explain what we observe. And slowly we make progress. The mysteries we face today will yield to future discoveries. New mysteries will emerge to take their place. The quest to understand the cosmos is endless, but that's what makes it meaningful. Thank you for joining me on this exploration of the universe's greatest mysteries. If you found this journey through space, time, and reality meaningful, please consider liking and subscribing to support the channel. Until next time, keep looking up at the night sky. Keep wondering about the darkness between the stars. Keep marveling at the fact that we, small as we are, and brief as our lives may be, can contemplate black holes, the Big Bang, and the ultimate fate of everything. We are the universe's way of knowing itself. And that's perhaps the greatest mystery of all. The cosmos is incomprehensibly vast, filled with wonders beyond imagination. Yet here we are, conscious, questioning, exploring. We stand on a small planet orbiting an ordinary star in an unremarkable galaxy, one of trillions scattered across the observable universe. But we are not insignificant. We are the ones who ask why, who seek to understand, who refuse to accept mystery without investigation. We build instruments to extend our senses, mathematics to extend our reasoning, and theories to extend our understanding. We reach across billions of years and billions of light years to touch the very fabric of reality. That reaching, that striving to know, defines us as a species. It's what drove ancient astronomers to track the motions of planets, what inspired Newton to formulate the laws of motion and gravity, what led Einstein to reimagine space and time themselves. It's what pushes us today to build gravitational wave detectors, particle accelerators, and space telescopes. It's what will carry us into the future, toward discoveries we can't yet imagine. The universe awaits, its mysteries beckon, and we, improbable as our existence may be, are ready to explore. Sleep well tonight, knowing that reality is far stranger and more wonderful than any fiction. The darkness above contains billions of galaxies, each a universe of stars and worlds. Black holes bend space-time into knots. Dark energy pushes the cosmos apart. And through it all, gravitational waves carry messages from the most violent events in existence, ripples in the fabric of everything. We live in an age of discovery. The tools and knowledge we have now would seem like magic to our ancestors. Yet we're only beginning. The next century will bring revelations we can barely conceive. Perhaps we'll detect dark matter particles. Perhaps we'll confirm the multiverse. Perhaps we'll understand what happened before the Big Bang. Perhaps we'll find answers to questions we haven't yet thought to ask. Or perhaps the universe will remain mysterious, its deepest secrets forever beyond our reach. Either way, the journey is worth taking. The quest to understand is what makes us human. And the, universe, in all its vast and terrible beauty, is worth trying to understand. Good night.